Okay, formal notes.
This meeting is being recorded.
I mean, I charge people, you know. Yeah, exactly. Working, trying to find that. No, my daughter went to the day to see back access. And I just don't know where she put it. It's really cute. Somebody needed it. Where did you put it? Yeah. There are no more snacks in it. It's not endless snacks. Sorry.
All right, I'm gonna go ahead and get started here. So thank you everyone for coming. I appreciate this. Everyone taking time out of a busy day for this. So I'm Jake Schmidt. I work for MindWare Technology. Because I'll go to that next slide. There I am, of course. And what we're going to go over today is just looking at a general brief introduction into the autonomic nervous system, its adaptability, going sort of through the physiological foundations, and then kind of ending up with behavioral interpretations. So just a couple things before we get started, though. We're going to have a lunch that's going to be held here. Are we eating here? In this location?
I believe.
Okay. Okay, cool. So we're actually gonna have lunch catered. We have food, drinks coming for everybody, so you're welcome to stay for that. That's gonna be from noon to 1. So for right now, we're gonna be going over, like I said, this brief introduction here. We're gonna go through some data acquisition, improving data quality, and then we'll actually look at multi-modal integrations, and stimulus presentation, different ways you guys can get feedback on participants, experience sampling, things like that. 1 to 4, we're going to have sort of an advanced analysis section. So for those of you that are doing the analysis yourself, or managing those that are doing the analysis, we can actually go through that and look at that at a sort of macro and micro level, and sort of compare how everyone's doing their analyses, and yeah, kind of we can go back and forth through specific paradigms you all have, study protocols, anything like that. So the 1 to 4 is a little bit more open for Q&A, if you will. Cool. Any questions before we get started? No? Okay. And then there's a session tomorrow. Would anybody be joining for that as well? That's here? Yeah. Okay. All of you. All right. Cool. So, and then also, who here has collected physiology before? Some of you, and then some of you have no experience, right? Okay. All right. Awesome. So I'll kind of try to tailor for that a little bit, but if anybody that hasn't no experience with it, please ask a question. As we all know, if you ask a question, it's likely that someone else has that same question as well. So please stop me whenever you want, and we can direct those right away. Okay, so what I'm going to do is I'm going to go into the sort of physiological backgrounds in the autonomic nervous system, and then sort of the implications on it, such as allostatic load, both on the parasympathetic and sympathetic nervous systems. So first, looking at these are sort of simplifications, if you will, but what we're mostly going to be looking at is sympathetic, parasympathetic, those two branches of the autonomic. And we know that it's really not proper to just observe one. We need to sort of look at both because they can both affect different physiological outcomes, and they're also not reciprocal. It's not that we have activation of parasympathetic and then a deactivation of sympathetic. These things can sort of co-activate and then deactivate at the same time. They can have any sort of combination in there. So when someone is looking at reporting something like heart rate, for instance, that's actually not a great metric of anything because you can have both sympathetic and parasympathetic contributions to that change in heart rate. What would be better is if we actually split different things up, such as heart rate variability, or looking at contractility for those two systems. So anyways, we have the parasympathetic and the sympathetic here. So again, the oversimplifications by quite a bit is we have the rest and digest and the fight or flight systems here. And so as it says here, this sort of dysfunction here we can see it specifically with the sympathetic dominance. We see a lot of that sort of negative health outcomes, both behaviorally and physically. So a very prolonged sympathetic drive is certainly very detrimental to our health. And so what we're looking to do is get something that's autonomic balance. And so in this adaptability, we can actually have the sort of resilience to overcome a lot of those stressors. And so that's what we're trying to target in a lot of cases. So anyways, this is a nice way, if we can do this, we can actually treat this as sort of a black box system. And so if we're actually running through our protocols, whether that's a therapeutic session or some sort of other behavioral interpretations or stress inductions, whatever you're doing to essentially help that participant group, we can actually look at some of these physiological outcomes, and then from there we can actually see if it's working. We can see if this thing is actually helping them, and we can actually individualize the treatment for a specific person. So by looking at simple change scores between statistics such as respiratory sinus arrhythmia for the sort of parasympathetic side and pre-ejection period on the sympathetic side of things, we can really build that picture there. Great. And again, if you have any questions, please stop me. Whatever you have, totally fine. Okay, so first looking here at the parasympathetic side of things, what we see here is we have the sinoatrial node. So this is essentially the pacemaker node, and it's a group of about 1,000 cells. They all fire in unison, and that is what's kind of keeping that baseline rhythm for us. Now, how this can change in addition to the sort of baseline rhythm is by vagal activation. So there's 12 cranial nerves. The 10th coming out is the vagus nerve, and that has projections to almost everywhere in the body. As you saw in the previous slide here, the organs that are innervated are sort of endless here. And so looking at this branch here, the straight parasympathetic side of things here, you can see that it has a lot of those projections out to all these different organs. And then sympathetically, we also have the sympathetic chain ganglia that are activating other organs as well. And so you can see there's actually a lot of cases where we see both parasympathetic and sympathetic contribute to the same organ. And later on, we'll actually see like why we actually want to look at the same organ ideally to get both instances. Cool. So going back to this right here, looking at sinoatrial node, we have sort of the parasympathetic regulation. So as far as a neurotransmitter is concerned, we're going to start with acetylcholine in the brain, and that's going to be sent down the vagus nerve, myelinated very quickly, straight to the heart, so it's a node. It's going to dump that acetylcholine on there, and essentially that's going to increase or reduce the sort of brake. So what the vagus nerve is really doing is it's kind of a brake of holding back the heart rate from accelerating. And essentially when we have deactivation of that, that's when the heart rate could increase quite a bit. And so anyways, that activation there from that acetylcholine is straight to acetylcholine right in the heart. So it's a very quick reaction. It's usually on the order of a couple hundred milliseconds. Whereas with the sympathetic nervous system here, we're going to start as acetylcholine, but we do need to make a chemical transmission over to epinephrine and norepinephrine. So that sort of time for that energy to be transferred over to those other transmitters makes the sympathetic nervous system quite a bit slower. So As far as the reaction of that, it's usually on the order of like 1 to 3 seconds. Sort of, there's some high error bars there, but and so anyways, point is that when we're seeing some sort of reaction parasympathetically, we're going to see something very quick. Sympathetically is going to follow that a little bit after that with some latency. And you can see here with the sort of parasympathetic side of things, we have the ability to slow the heart rate by the activation of dumping more acetylcholine on the synovial node. And then sympathetically here, we can actually see that there could be an increase in heart rate and then a decrease in heart rate variability. So the changes from one beat to the next. Okay, so and then the left ventricle here, going off to the sympathetic side of things a little bit more. So the left ventricle of the heart is sort of that last chamber that the blood is going to be focused into before it goes out of the left aortic valve. So when we're looking at this thing, the left ventricle is essentially pumping that oxygenated blood into the body. And then, yeah, from there, that's kind of the start of our sympathetic activation period for pre-ejection period. I'll go through that in a little bit here. But essentially, the sympathetic side of things can look at how hard the heart will beat and how much blood is pumped out. And then the parasympathetic side of things is like how fast is the heart going to actually beat, right? So there's really an electrical component and a mechanical component between these two systems, if you will. Okay, and first thing real quickly here, so how to actually measure heart rate variability, and very specifically, there's a little bit of a specific point to bring up here is heart rate variability. What we really want to say and how we want to report this and look at this is high frequency heart rate variability. So it's HF-HRV. It's a little bit wordy to say all the times, but when we're looking at that kind of thing, that's really what we're concerned with. We'll see in a little bit why that's really important, but essentially, as I talked about before, because the sympathetic and parasympathetic nervous systems can affect heart rates, we need to isolate them. We need to see, okay, like which one is affecting, you know, the heart rate variability. By passing the ECG data, we have these beats here, and we can actually see they're changing due to the respiration. So this is respiratory sinus arrhythmia, changes in heart rate due to breathing. And essentially what we're doing is we're going to take these data, we're going to find the time in between them, which is also known as the interbeat interval. And then we're going to pass those data into a Fourier transform. So what an FFT is going to do is it's going to take that time domain data and it's going to put it into spectral components or frequency components. By doing that, we can actually look at a higher frequency, sort of like 0.12 to 0.4 in resting state adults. In that range, we know that is just the sort of parasympathetic vagal activation. We know that because of that sort of slow sympathetic thing couldn't really activate that quickly, right? So anything above 0.12, again, in adults, must be only parasympathetic. So that's really why we want to look at high frequency heart rate variability. Heart rate variability at sense would include everything. And in the lower frequencies, that information, that power in the lower frequencies could be either. It could be sympathetic, parasympathetic, and we can't tell the difference because they both can work in that realm. A couple hundred milliseconds parasympathetically, and then usually a couple seconds sympathetically. So anyways, just kind of thing there. I don't want to see, you know, HRV on its own and anybody's thing there. Please do HF-HRV, yes.
Question. So does this mean that ECG does not give enough decisive information from the sympathetic?
Exactly, yes. So there is a statistic right there, thank you. So high frequency, low frequency ratio. So this is something that historically people use to sort of get that balance within just looking at the ECG. The problem is that there's not that reciprocal approach I talked about before. It's not like sort of the Walter Cannon approach of like if the sympathetic goes down, parasympathetic doesn't. Now that is true in certain situations, such as like an orthostatic stressor, but in other behavioral realms, it's not the case because again, we could have sympathetic activation, which is going to, you know, potentially increase that heart rate. But it could also be the case that there is just less acetylcholine down in the atrial node. So then in that sense, the heart rate is going to increase as well. So we just wouldn't know the difference between the two. So this high frequency, low frequency ratio should really not be used. It's really been debunked over the last 15 or 20 years. So if you ever see that in there, it's a nice, like a sort of general overall autonomic activation, but it's really not a complete picture there. So really for the sympathetic side of things, we really want to get some sort of other markers such as impedance cardiography, which I've been talking about, or potentially escape conductance. Awesome. And then other way we can look at HRV is going to be the PPG plasmography or photoplasmography. So I think we're all familiar with that one. That's something like essentially a light emitting diode. It's going to put that sort of light into the tissue that you're putting it over. It's going to diffuse, and it's actually going to look at the oxygen in the blood that is over that tissue. So essentially what we can do is you can think of like your watch that also gives that for you, right? It's giving you heart rate variability. It's going to tell you like how stressed you are just from that, which is really, way oversimplification from what I just talked about. What it's looking at is actually seeing like when that oxygenated blood from the left ventricle reaches that tissue or that portion, versus when that oxygen is actually diffused across there. So it actually can see that in a sort of normal distribution curve of when that blood arrives, oxygenated, and when it's diffused. And so then it's essentially picking up on that peak of the max point that the blood is receiving with the most oxygen, and it's saying that's the beat, that's when it occurs. The problem with photoplasmography, not only is it only parasympathetic, but it's also just not rich enough. So when we're looking at that oxygen arriving, it's not this like really sharp, and precise point, this sort of fiducial marker of this is when that beat occurred and this is when that beat occurred. It's more of like a rounded curve. Almost you can think of it as a little bit more like respiration. And milliseconds matter, as I talked about before, with the parasympathetic regulation. So if there's not a very defined peak and there could be multiple points across the top of where that could occur, it's very ambiguous as to which point we should choose. And if milliseconds matter, finding the same point between beats can be very difficult. So another consideration here with PPG is that it does not control for any sort of arterial stiffening. So if essentially we have the arteries in our arm that are going to stiffen, that's going to increase that actual pressure, and that oxygen is going to get there a lot quicker. If you can think about like a hose that is very loose, it's going to take a while and the pressure is going to be low. If we strengthen that out, it's going to go through very quickly. So just another sort of thing to consider if we're looking at just PPG. Now, there's quite a bit of understanding here that, using a MindWare system or something, and people come in the lab, we're hooking them up, that works. If we're going to send them home and they have, we have a lot of participants or something, we can't use the MindWare system, right? Because that's, a little bit too much and too involved. And so sometimes we just watch and that's what it is. And we get something, we get heart rate variability, but just kind of be, a little bit understanding and set your expectations that it's a little bit limited because we don't have that sympathetic side of things. As far as measuring the parasympathetic nervous system, a couple different things we can look at. Again, high frequency heart variability. That's where we can observe the phenomena, which is RSA. So high frequency heart variability is a tool, and the tool is being used to observe the phenomena. It's not the same thing. So even in some literature, you'll see HRV, HF, and then that sort of slashes, and it's the same thing. But just making that distinction is very helpful. This is going to be based in that frequency range when we're looking at that respiratory sinus arrhythmia. So again, we're going to take those time data, pass it through a Fourier transform, essentially taking that data and breaking up to its spectral components. So what frequencies make up that primary frequency. And that's how we can isolate the parasympathetic side of things. We can also look at time domain. So let's say that we're designing a study and maybe we only have the ECG signal, or maybe we do have multiple different signals we're collecting, but we don't have a form of respiration. So because we're looking at respiratory sinus arrhythmia, we need to control for respiration. We need to make sure when we're collecting ECG data that we're also collecting respiration, because if you essentially hypoventilate, breathing really fast or very slow, you can actually invalidate RSA. In those instances, that could be a problem. And so if we are looking to report on something and we do not have respiration, I would definitely recommend you, at the very least, focus on RMSSD. So that is a time domain measure. What this is going to be is the root mean square of successive differences between beats. So what that's actually going to do is allow us to normalize these data and the time between them and look at it in a time model. Now, if we do that, it's going to include everything. It's just heart rate. It's including the entire time period under this. So, do know that you're also going to be looking at some sympathetic contributions within the RMSSD, but it's usually overwhelmingly parasympathetic in that sense. But do be a little cautious of that and understand the limitations of RMSSD. However, in most cases, the respiration does not have much of an effect on this statistic, and so if all we have is ECG data, I would likely lead with the RMSSD, and then also reporting RSA to see if there's any sort of correlation between the two. But I would say you're probably in the realm of getting a revise and resubmit here if you try to do RSA without the respiration. In some cases, especially for those of you that are looking at children, very young, we can get by with this in a lot of cases. It's just we can't put a respiration belt on them. They're going to pick at it, they're going to rip it off or something like that. We weren't able to put all the stickers on for impedance, so we can't get a respiration that way. But yeah, just kind of be aware of that. That is usually a sticking point that we also get respiration when we're collecting these data. I'll go for this in a little bit later, but when we are collecting impedance, so if we look at this model right here, as far as collecting ECG, we normally follow a lead to configuration. So there was a principle done by Eindhoven, so this is about a couple hundred years ago, and he drew a triangle and got a Nobel Prize, and pretty jealous because I think I could draw a triangle and step in and do that one for him. But anyways, it's sort of looking at the electrical vectors of the heart and its conductance. So if we actually have our heartbeat right here, the sort of projection of the electrical vector is going to be coming down these sort of Purkinje fibers in this general direction. So it's kind of splitting up this way. So we're going to collect that sensor right on the sort of left rib to get that signal coming straight on. And then we're looking at the sort of bipolar differences by putting the other sensor on the right clavicle. If in some cases you all are collecting population where we can't just put sensors all over because it's sort of sensitive population again, then we can do different configurations. So again, there's the triangle here. So if we look here, we're completing this triangle between these two sensors and the ground. We can also do a lead 1 configuration, or we can actually look at a lead 3, which is these two and that one there. So the 2 clavicles is possible if that's easier to put on there. If it's something where we really can't touch people that much at all, we can also collect it from the wrist and the lower ankle. That's definitely possible, and we're still sort of completing that triangle, if you will. Do be aware that you're going to get a lot of motion artifact when doing that, but it's certainly better than nothing if possible. So, but in normal instances, if we can collect this normal array, that would be best. And then there are 2 white sensors that we look at here, which is going to be the 2 for impedance cardiography. There's actually 2 in the back. They're putting a constant electrical current through the chest, and then the 2 sensors on the front are receiving that signal. And essentially what's happening is as that electricity is going through the body, it's passing through a couple of organs, primarily looking at the lungs and the heart. So that electrical signal is going to try to find the path of least resistance as it's going through. So that's going to be blood, and it's specifically in the aorta of the heart. It's going to be the highest concentration of it. So that electrical signal is going to focus in on the aorta because of that very low impedance or low resistance. And then it's going to pass straight through to the sensors on the front, right? Those are the actual ones that are receiving that signal. And you can actually see here, there's little points here where the sensors go on the back. And then we have the front ones, of course, that are on the front. So if there's blood in the heart, we have very low resistance. And so that signal passes straight through, and we can actually see that. If blood has been ejected out to the periphery, so now we're going through muscle and bone and tissue like that. So there's a lot of resistance, and we can actually see that in a very sinusoidal sort of fashion of when that blood actually enters the heart and when it ejects out. And so another benefit, as I talked about before, is the respiration here. So if we're looking at and doing impedance cardiography and HRV, they pair very nicely because it's the same organ. Again, it's the sort of parasympathetic, dropping acetylcholine on, and then we have sympathetic chain ganglia over on the left ventricle, which are controlling contractility. And so pairing these 2 together, we don't have to worry about something like a stress response that is only organ specific. If something goes just to the kidneys and then we're looking at the skin, those 2 do not have to have a one relationship. Again, they can kind of coactivate, deactivate, something like that. So very sort of historical approach would be to look at ECG and skin conductance, right? That's parasympathetic, sympathetic, but those are different organs. So if we see something like a sympathetic activation of the skin, we can see absolutely nothing of the heart. So again, just sort of relaying that why these 2 are helpful. But going into impedance a little bit more, as that we have that constant current go through the chest. What it does, electrical vector is also doing is going through the lungs. And we're breathing in and breathing out, that sort of past the lungs is expanding and contracting. And so it's actually taking that electrical signal longer to go through when it expands and less time to go through when it's contracted. So what we can do is we can actually see that change in respiration because of that change in the volumetric properties of the lungs. And we can actually derive respiration from it. So this is, certainly for those of you that are looking at any sort of children, adolescents research, those sort of sensitive populations, sort of the non-neurotypicals, just having a very tight respiration belt around their chest is not really a great option. Whereas if we're putting the ECG on with a couple more sensors, we can derive respiration from the impedance and sort of a bonus to the sympathetic marker at the same organ. Any questions on that? Let's pass out because I've been breathing. No? Okay. Okay, again, here, just going into this a little bit more with the PPG. So here's a finger sensor that we could use as well. And just saying about before, this is inexpensive, it's less invasive. So if it's the best we have, it can certainly be used. If anybody is looking to do something like a experience sampling or something that people are taking home to sort of wear throughout their day, I can certainly make some recommendations on some things that can be used that are research grade, that have the correct sampling rate, things like that. And even those that can be used to import into our analysis as well. So if afterwards someone needs to do something like that, just talk to me and we can look at some options that might be best for you. But we can do it here as well with MindWare by using the finger sensor or ear clip to look at that PPG signal. Yeah, and I think I went through this before. Just talk through my slides a little bit. And then looking at the impedance just a little bit better here. So these are the sort of two sensors that we talked about before. So what this is going to do is really being on that fourth vertebrae, so that one that sticks out in the back of the neck. And then we're going to look at a little bit lower on the back. What we actually do is we place the first ones on the front first. So one is going to be in that jugular notch. And then over here is a xiphosternal notch, or a xiphoid process. So it's essentially the two parts on the outside of your sternum that push in. Now, do be aware, if you're going to have any speaking within your task, you'll actually want to normally set that positive impedance sensor off to the right on the clavicle, just so it's not vibrating every time they're speaking. Also, another note here, just as sort of looking at studies on here, if there is going to be a significant amount of speaking in your task, we will want to control for that. We want to actually take a speaking baseline in addition to a normal baseline. This will certainly be, reviewed and critiqued quite a bit if you have a lot of tasks sort of speaking and you didn't do that speaking baseline. Something for that usually is something that I can read off. It's like a script or something, and so it's standardized. It's for every person. But just a quick note on that. Okay, as I've been kind of alluding to here, we have the different markers from the impedance choreography, so pre-ejection period. So we have a couple different components. So we have the P, Q, R, S, and T. So the P wave that we see here is the H rate of the heart depolarizing. The QRS is that actual electrical contraction of the gradient going over the heart. And then the T wave is the ventricular repolarization. What we're primarily focused on and care the most thing about is an RP. It's also an R spike. And what we're going to do is we're going to use that to determine that's when that sort of beat occurred, and then look at that same marker, if you will, over time, in the time between them. What we're going to do, though, is in addition to that, we're actually looking at the pre-ejection period here. This is the DZT from the impedance waveform. So impedance is actually going to have two things we're looking at. This is the first one's going to be Z0 or Z naught. This is the raw impedance waveform that includes blood flow plus the respiration. So it's sort of like a wave riding a wave, if you will. And then once we take the first mathematical derivative of that, so the sort of slope change y equals mx plus b, we can actually get the DZT again being that first derivative. So what we can do here is we can actually see if the Q point, if that was the onset of the sort of activation electrically of the heart, when did that left aortic valve open, which is, we can see here B is being represented, and then the latency between the two, so Q to B, is going to be our pre-ejection period. And so that's the point at which the blood is going into the left aortic valve. I'm sorry, the left ventricle, it's building up. Once the pressure inside that left ventricle is sufficiently high enough to have the valves open up, the blood ejects out, and then we actually see that point here of the valve opening up. And then this Z point, or sometimes seen as C, is the point of max blood flow to that left aortic valve. So if we can look at the start electrically here and start here of that opening, we can get this time before the blood actually ejects. So this is known as a pure sympathetic marker in a lot of cases, because it's only looking at the time and contractility. So if the heart was told to be at Q, the sympathetic nervous system has the ability to delay or speed up the sympathetic side of things by changing when that the sort of timing characteristics of when that left aortic valve opens. It can also change how hard that heart is beating, which would change how much blood is pumped out each beat. So this pre-ejection period here is a nice, again, a sort of sympathetic marker. So if we were comparing the two, respiratory silent state arrhythmia, RSA, and pre-ejection period EP is a sort of perfect match between the two. Another marker that is used very commonly is left ventricle ejection time. So that's what that is doing, is looking from the opening of the left aortic valve at B and the closing of the left aortic valve at S. This has been shown in a lot of cases to actually be a better sympathetic, more accurate sympathetic marker than pre-ejection period. The problem in practicality is just that the closing of this valve is in a lot of cases very non-distinctful. It's very like sort of flat line, and the sort of chalk point to find a very precise point is not always observed. So pre-ejection period is normally preferred in that sense, but if you have such a population where the data are very clean, you get that X point reliably, certainly you could focus on that as well. Okay, and then last thing we haven't been talking too much about, but I will cover a little bit here, is skin conductance. So again, this is a nice sort of easier way to get that sympathetic of things. And as far as electrode placement here, we can do that from the hand, the fingers, and then also the bottom of the feet. I'm sure a lot of you, unless you're looking at sort of the infants and toddler stages, the bottom of the feet is pretty invasive. It's not something we're going to want to do. But the idea here is that we're looking at two types of sweat glands. So one is apocrine. Those are like thermoregulation. They're just activated trying to pull us down. And then we have the eccrine or acrine sweat glands. The last one is what we're very interested in this case, because those are only activated when we have a sympathetic response, so sympathetic activation. Those eccrine sweat glands are found in isolation on hands and the bottom of the feet. Everywhere else in the body, you're going to have both. So anyways, those are the kind of best locations for them, but as I said before, there are some caveats here. As you can see, activation in the organ of the skin and not the heart. But with that said, essentially what we're looking at here in a lot of cases, there's two main outputs that people are interested in. One is going to be the level, so just what is the actual level of the skin conductance, so we can just look at the baseline skin conductance level, and then we can just do a change score between that and the condition or the stress response. Another thing that we can look at is skin conductance responses, or SCRs. So this is actually focusing on an SCR right here. So we were going to do a study in which there is stimulus presented at this time here. Let's just call this time 0. What if there is going to be some sort of spontaneous sympathetic activation that is seen as a rise in this level? So we actually see increase in sweat glands on the hands. So, and you know, those of you that haven't collected it, if you've ever gotten very nervous or something, you can tell that your hands and bottom of your feet are getting a little clammy, and that is picking up on that response there. So anyways, these SCRs, they can be non-specific. So that means that as we're going through the protocol, we see these sort of, again, like sort of spontaneous SCRs that occur. In those cases, we can just do a count of how many occurred within, let's say, the baseline period to your condition to a recovery. And if we're doing some sort of stimulus presentation, such as they're using a stimulus box, such as I have a Raponda one here from Cedrus. So they're actually interfacing the response pad. They're doing any sort of computer-based tasks. Then we can actually put markers within those programs that would say this is exactly when that stimulus was presented. And again, this could be an electrical simulation, this could be acoustical, so startle, or something visual as well. Then about 2 to 3 seconds later, again, the sort of that period for sympathetic activation, we would see a rise in that signal. And then what we can do then is we can say it as an event-related skin conductance response, or ERSCR. Okay, so choosing a system here. So assuming that everyone here does not have MindWare, we're looking at different systems. These are just some different criteria that we feel we do really well. But of course, in looking at for anything, we want to make sure that these are important sort of components of the system that you're looking at. So one is the big one here that if we look at a lot of different systems is the transparent signal processing algorithms. So in MindWare, we have everything's completely transparent. Every algorithm, how the data are processed and handled through our acquisition and analysis is completely transparent. If you go to our support site, which I'll show you a couple images of later, you can actually go through these guides on the 3 different systems I've been talking about, and it'll give you the algorithms, the papers that references everything right there. When we're not doing this, we're looking at certain systems where they're like, okay, we're going to output something like the respiratory sinus arrhythmia or the IBI, but we don't know what algorithm we're using to get that. That's a lot of problem for consistency and study replication. So do make sure whenever you're looking at something, again, either the acquisition hardware or the analysis software, that you do have access to the raw data. Sufficient resolution with sampling rates, the analog to digital resolution and bandwidth. So this is where a lot of those sort of PPG sensors of getting the heart rate variability fall short. So such as like the watch or the finger sensor I showed you before, in a lot of cases, the sampling rate of those are quite low and something that's not sufficient for high frequency Nervy. It can also be done with ECG. So there's also some watches right now, rings and stuff, where we can actually make 2 contact points, and then we can actually get that actual ECG signal from those. But they still fall short in most cases on these 2, where we don't get access to raw data, and then the sampling rate of those is not sufficient. As far as the minimum sampling rate for everything you should be looking at for the highest frequency is going to be at 250 hertz. So 250 samples per second. If you are looking at anything below that, that's usually going to be a revise and resubmit, sort of invalidating that measure just because the sampling rate wasn't sufficient. So keep an eye on that, 250 hertz or higher. Having something that can certainly do multiple measures in the same system. With a lot of systems that you'll see out there that have distributed pods and things like that, they actually don't synchronize perfectly, even though they say they do. And so making sure that we have a unified system that can collect everything is actually very important. And then we see here just like the sort of ease of use here. So this is where something like a watch or a band or a shirt or something becomes a little bit better than putting electrodes on everybody, because it's easier to put on the participants. In a lot of cases, we have 30 minutes or an hour with these participants. We have to get it done in that amount of time. And so making something very easy to apply to them, and also not creating stress in itself by putting on the sensors is very important. This right here, which we can talk about a little bit later, if anybody's interested, is ensuring that we can synchronize very precisely to different systems. So is anybody doing an EEG question here as well? One, we got one? Okay. 2. So one of the things that we want to look at commonly with that is event-related potentials, or ERPs. So essentially that's the necessary correlation between the ECG signal and EEG. In those cases, we want to make sure that we have something that is truly synchronized to the millisecond. And this can be important for a lot of different things, such as eye tracking, apnea, things like that. It all is important that we have a very precise marker. Another component here with the Cedra system is we have a stim tracker, which I can take out in a little bit. Essentially, it's a piece of hardware that has the ability to plug different pods into the back. There's one for every system pretty much out there. So if you're looking at different EEG systems, eye trackers, different physiology systems, there's a pod for that. It will make sure that those are all synchronized exact millisecond. Cool. Okay, and then just going through a data collection analysis workflow. So here. So the actual physiology data collected by MindWare in this case with a mobile device. We can also synchronize with something that's such as like the Tobii eye tracking glasses, and we can also implement an audio video collection for sort of that affective behavioral for those of you who are doing that sort of analysis. And we can synchronize all those things perfectly. The audio video data can be loaded into a atomic behavioral coding software such as Mangold's Interact software. There's also the Novus Observer software for those of you that use that. And in that case, we can actually create a coding scheme for all the different expressions and things that we're interested in. So if we're doing, let's say, a parent-child interaction, and we want to know every time that mom looks away from baby, what is the physiological reaction on the actual baby, and what does that change? So we can actually look at that and essentially come up with the coding scheme. We're like, okay, a keystroke of every time mom looks away. We create these different event codes, and then from there we can look at a lot of very interesting statistics. And once we create those event files, and doing the eye tracking data as well, we can actually load the event output files of when those different keystrokes were occurred by that experimenter, and we can load those files directly into our analysis. So then we can ask really complicated, rich questions such as, what was the physiological reaction every time that, essentially mom looked away from baby, for example. Okay. And then just going through a protocol here, and again, at this point, if anybody wanted to ask any specific questions on the protocols they're proposing, currently doing, or anything like that, we can certainly talk about it. Just going through a very common one here, just for those that are not completely familiar with it. So in this case right here, what we're looking at is implementing a couple different things, but essentially looking at the stress inductions here of the hand grip cold pressor and pain pressure test. So in this case here, it is nice to have this sort of pre-test evaluations. You're going to have your consent forms, all those different things. Always collecting the height and weight is very important. The hip, waist, arm, finger sizes. So if we are looking to collect something as a continuous blood pressure signal, we want to get those statistics as well. And then the maximum hand grip force. So what in this component is going to be doing, we're looking at hand anemometer. We can actually have them squeeze, and then we can actually conduct that sympathetic activation at that level. And then we have some other different surveys here as well, which can be seen at the bottom here, which are very helpful in a lot of cases if you all wanted to implement those ones. After this pretest evaluation, we're going to implement a rest period. Something like 5 to 10 minutes is ideal. The minimum I recommend doing is about 3 minutes, but that's very dependent on the study you're looking at. Again, then we're going to be looking at a baseline period after that. And right here, also we're looking at a deep breathing exercise, so we can actually control and create that respiration sort of baseline period. And then running into a hand grip test, that hand anemometer test, and then immediately going into a cold pressor. So cold pressor being, putting our hand in an ice bucket, seeing how long someone can keep their hand in there, with pain pressure tests, and then finally following with a post-test evaluation. Any questions on this right now, or anything to talk about? Yes.
Yeah, I wonder if you could go into more specifics behind measuring something like hand grip force. So you mentioned that it was because of wanting to get a sense of their sympathetic nervous system activity. I just wanted to know a little bit more about that.
Yeah, so essentially what we're doing there is we're looking at the blood flow and everything in the hand grip test. And so by looking at that, we can actually see what is the maximum force that someone's able to do. And then we're going to then, in that hand grip test there, throughout different tasks, they're actually going to see how that is evaluated within that. Because essentially we can actually see when it's a activation, they can actually grip that a little bit harder, essentially.
Oh,
Yeah.
okay. So this is very specific to this sort of scenario of like where this is kind of one of the activities, right?
Yeah, exactly. Yeah, this is example one. I mean, there's a lot of different ones we could do. I mean, there's the TSST, the Trier one. Certainly, that is another very common stress induction one for sympathetic activation as well. So, yes.
Can you talk more, a little bit more about the height and weight? So how's that?
Yeah. So height, weight, general like activity states, physical fitness. Those are all things that in a lot of cases reviewers will want to see that you control for. Just any sort of anatomical differences can affect our physiology. And so just ensure that we're controlling from them later on. So collecting these data, and then as we're outputting statistically, we can see if we see any sort of difference within our group for those that have like something like, again, 3 standard deviations from the norm. We can actually look at them. Is height and weight have something to do with it? If no, include those people. If it does, then we're going to throw them out. Also, in addition to here, something that is important to really pre-screen is for any sort of drugs that they might be taking, recreational or otherwise. And so, anything that we're looking at very commonly, such as like MAOIs, any sort of SSRIs, those sort of different things are something to look at, but it is not something that we can normally exclude from our population pool because that would be like 70% of the people. But certainly any of those different things that we're looking at, any sort of amphetamines that might be taking, and again, any sort of recreational things, very helpful to at least control for and look at a little bit closer, yes.
Do you have guidance on caffeine consumption, whether it should just be measured as a covariate to include in analyses, or trying to encourage participants to not drink coffee that morning or soda or whatever?
Yeah, I am more of a proponent of the former thing, is the first thing you said there, because there's a sort of understand that caffeine will certainly affect their physiology. Yeah. That's well known. But if someone drinks coffee every morning and then you tell them not to drink coffee, then that can actually have more profound effect on them. Really not observing their normal state. So I would just control for it as covariate potentially. Yeah, cool.
Thank you.
And just the survey question, like how much, ask them.
Yeah, what's your usual?
Yeah.
Okay.
All right. Yeah, I guess so. From this point forward, I have a couple different things here to go through with different services and stuff that we do here at MindWare. And then we have the electrode placement here. So at this point here, this is something we're going to mostly do tomorrow. So we don't have to do it today, but if anybody is not going to be here tomorrow, we can. But at this point here, we can take a little bit of a break. But if anybody's interested in actually applying the sensors today to kind of see how that works, we can certainly do it at this point here. Does anybody want to do that, or is everyone able to come tomorrow for that? Nobody now? Everyone hooked up? You get live streamed? Sure? Okay, cool. All right, then we'll go through this a little bit here. And then if everyone wants to take like a 10-minute break right now, then we can come back and then look at a couple more things and then go through maybe a more informal discussion if anybody has any more questions. And go from there. Okay, cool.
There's like a lock, but I know that there's also a rest place. I mean, I saw yeah.
Why is it?
It's just a special.
And also I did.
Okay,
So
okay.
it's like something's wrong with your coffee, my friend.
Oh, there we go.
I just have a little quick question. So, one of my dissertations about doing that for kids who are like 6. Do you have any comments about the number of electrodes or? I don't qualify at least in one time for like a smaller one that's just 2 electrodes. Do you have any comments on like how well they tolerate?
What is the population of 46? Is it just
Yeah.
typical?
Yeah.
Okay. Yeah. So yeah, I mean, the less you can put on, the sure the better. Is it something that where you're just looking to get ECG collection, or you're looking for?
I'm not super sure yet.
Okay. So, when would you actually be looking to do this? Is it somewhat
Not for the fall.
Not for the fall. Okay.
I haven't submitted the IRB yet, so I haven't, through this time.
Okay. So you would actually think that data collection could occur this fall?
Yeah.
Okay. So there's something that I'll cover a little bit later that might interest you. It's a new thing we're talking about. There's like a shirt that we put on. So it's not going to be ready until likely the spring of next year.
Oh, yeah.
So I don't know, but yeah. Other than that, I mean, as far as different devices, I
That's
mean,
good though.
they're going to be coming
Yeah.
in for in-lab.
We have another Friday.
I don't know, so, I know.
Is it like,
I guess kids are well,
Yeah.
like starting right now, so.
although this came straight from their kids, but I think.
Right.
Talk to you.
They were motivated. They were like,
There's a Zephyr shirt. I don't know. I could or it's something where you just
When they fill out questionnaires in the lab, their answers are different than the answers they give in the face. So they are technically, they were eligible.
yeah.
it's fine.
And I brought it up to them, it's like, maybe this is an interesting.
It is an interesting
Right.
research.
So now I'm saving all the pre-screeners in the shared drive, so I'm gonna be.
Right. So there is something if
Loneliness
you
of-
I have doing that. There's a
They said it
just
Yeah, or if it's
professor
like
that
that
I walked for a
they're
while.
filling it out.
She actually created a octopus.
Yeah, and like.
They feel
Yeah, just like shows
Yeah.
Michael.
Been using it a lot being as like a researcher and their parents.
Yeah.
Like felt empathy. And then the lead table.
I don't know.
But I mean, that's
We're
a
getting
very,
such-
we're getting
other parents.
Really
and IRC like,
They did follow
I
the.
forgot as much.
were doing-
So
but it was
it's always like that would be great. I don't know if that's possible, but if you did that, then you know you certainly should get like our
All
mobile
the
device
things that we've become.
and get the actual infusion. So a good approach. But after that, I think like there is the Polar Watch, which is really nice.
Yeah.
And that kind of again, it's really good data, and it's like sampling rate. I think it's good on that. So yeah,
Oh my gosh, it's June 3rd. That's not
that would
okay.
work. Yeah. So just use the selection now. Yeah, it would. But the problem is it doesn't have respiratory. So if you look at RSA, like stuff. Then you're gonna kind of like a respiration. They're gonna disagree with that. So yeah, you know, both devices. I just thought get maybe good with like getting the application on and the confidence and getting them on quickly. Because they should only. I mean, I've done it. We had like sort of competition, but it's like 68 seconds. Like,
good.
come on, so like if you can get that loading on.
In 68 seconds, all electrodes, like, it's a lot.
We have an
Like,
internal challenge.
Like,
Yeah.
and EPA.
Yeah.
It's like, what goes against out,
Wild.
something like start implementing.
So you're not doing the little kids, right? Like, you're just.
No, it's just
Yeah.
like a minor competition. Yeah.
We did it with, we did, grad study.
That is a great time.
And children, level, yeah.
Yes.
Stop fighting me. I'm aiming for 4 to 6 in my last presentation, so that, we did a 2-year-old, but I got lots of tricks. Okay, cool, okay, bye.
Are they really?
Yeah. A lot more time.
Yeah, if you wanna, I mean, let's just look at some pictures and, you know.
She's so fun.
Just figure it out.
Yeah.
Yeah, of course.
You'll have more info than me.
Less than,
Oh, you can put them all out. You can, so yeah, okay.
But it's a big part of it.
Yeah.
Yeah, it's like, we kind of call ourselves like the behavioral.
With 2.5.
And exercise and food intervention. I also do, and it's the CAMS have the positive test series. It's like every task, especially every task.
Yeah.
I look at that, and I've done that with the mic guitar, like your guitar.
Getting you
Some of the tasks you do, like any task,
Yeah.
much more like when I have a skin
turn around for hero, you gotta get super
like
far.
they're talking about I see, yeah, I like having. I saw a lot. It was an emotional free call on somebody being compared to the true social.
When you like a lot of, if you watch these videos for social, they have on
The math part versus the interview part.
I always tell people like,
Have you ever done that? So it starts with like, well, what is more you're like,
in my
math job, and then I bring you in together, you have a 5
we
week.
didn't have a
Yeah. And then we have a lot, then you have a 5-minute question and answer.
and then it was like.
Sorry.
Also, man, you're good. I just.
Sorry, women.
Yeah, I think it's, you know, I think people don't fix that. I love that. Yeah, I will also add
So
that.
there's like, there's so much, everybody.
We did find somebody in my time. Yeah, yeah.
Then we select like, total, on the top, to live the cortisol level, also like for an hour. We also, because I mean, collect the 24 hours out there. Great picture.
Yeah, absolutely, yeah. And then, with the mobile devices, there's a. You need to
Dr. Lucero, I work with, and we also have, the name Nancy and there's Dr. Charles Stevens.
Yeah, yeah.
He's on it.
Yeah, absolutely, yeah.
And then the commercial. We were getting.
That's just on SY, but usually if those are
Different flavors. One would be like, this other
fancy
very.
time, just the tires and the Allen.
Time.
Well, and also like the question, and then we're also measuring fever, yes. No, actually, yeah.
This is your phone. What? It's a good thing. It's a good thing.
Yeah.
Oh my god. Yeah.
I'm looking forward to the next meeting.
Yes.
Serious, really strict.
I don't think. I'll look it up. I don't think it's. I think it's. You guys keep me young.
Yeah.
Actually, you have to get.
I love that. I don't like. It comes today. We're gonna cover. I'm gonna start like doing like, yeah, weird facial expressions. Yeah. The dictionary. Trying to be so still.
Yeah.
Here's the dictionary. So it's really a compliment. Oh my god. I love this. It's a good one. It's like robust, but yeah, but like yeah.
All right, everyone, go ahead and get started again. Are we missing somebody or is someone said right? Here we are. Cool. Started. Okay, so we'll save, I guess, that for tomorrow. Okay, go through a couple different services and sort of new products coming up that might interest everybody here, especially. So just so everyone's aware, we do have our analysis software and go through data cleaning. Those of you who have done that, it certainly does take some time to go through those. And another service we do have available is we actually can clean the data for you. In a lot of cases, there's some IRB regulation that you'll have to, look at this kind of thing. But as long as you can send us the de-identified data, we can actually go through, meet with you during a discovery phase, understand your protocol, review just a sort of random amount of some of your data, and then we'll actually go through with you and give some sort of preliminary interpretations on how the data can be used. And then we'll actually go through and start cleaning the data. At that point in time, you are getting sort of back and forth with your data analysis specialist. And then when we're done, we actually give you the edited data outputs, very detailed notes on every single edit that was made, why that edit was made. And then we provide an exit consultation with some preliminary statistical results. And yeah, I go from there. So if anybody is interested in that, let us know. And we can certainly work that out for you. Another thing here that to just look at is our laboratory design protocols. So even in the absence of physiology, it says here, we actually are very well experienced with sort of laboratory design applications. So if any use that we're looking for a very sort of integrated multimodal integration suite, including the audio video I've been talking about, our physiology, eye tracking, all kinds of different things. We'll actually work with you and create an actual very detailed lab implementation involving computer systems, all these different things. So certainly let us know if that's something that you are outfitting your current lab space with. Also, just where we are having a full, this is sort of the light version, just with just Jay, but we're having a full psychophysiology seminar and workshop here coming up August 8th through 10th in Columbus, Ohio. So if anybody can make that, we still do have a couple registrations open. So certainly if you want to, you can go to our support site to look at that, or you can certainly email me, and I can let you know a little bit more about that. But one of the things that's great, we actually have our scientific advisors here. So we have Gary Bernstein, who's like literally wrote the handbook of psychophysiology, present, and we also have Greg Norman, who was sort of in the lineage of Gary Bernstein and also John Cacioppo. So it'd actually be our main presenter there. And what we'll actually do is similar to this. We'll actually go a lot more deep diving into the scientific foundations and backgrounds of everything we're talking about here. And then we can actually do a data collection, analysis, feedback results, and everything like that from our actual advisors. So if anybody can do this, I highly recommend it. And yeah, it's a great experience, 2.5 days on this. So certainly let me know if you're interested in that. Finding additional sort of information here. So our support site is support.mindwaretech.com. You can also just say MindWare support in Google or the first link. But in the actual training here, you can see that there are different situations we can do. So complementary ones, this is happening right now. We also have online paid sessions. And there is actually a link within here. So those of you who have purchased a MindWare system and you have the training from us, what you are eligible for is perpetual complimentary training via Zoom. So, as you go on, you get students that are coming in, and this is a really nice way to kind of offload the sort of standard approach of data acquisition analysis to them. After they're done with that approach, it's nice to kind of bring them into your fold for the study-specific kind of things. So, again, those of you that purchase stuff and the training, you are eligible for that. There's no weekly limit use. You can use it every day if you need to. Students can sign up on their own. It's not like it has to be a lab meeting and sort of thing. So within the actual training section, you'll see that, and you can sign up right there. And this is just going a little bit more into the training guide. So if you haven't been there, there's a really nice introduction here about, all about ECG, for instance, like going into what is the heart, all the way down to actually editing RSA data and such. So there's no login or anything, so if you do want to check that out, that's a nice source. And then we'll have all the supplemental articles and references at the bottom of those as well. Okay, so something I want to talk about that we're very excited about at MindWare is we're coming out with a brand new technology line. And so for those of you that are doing any sort of adolescent children acquisitions, especially those that are interested in doing experience sampling, sending participants home, something they can actually use outside of lab. We are working on that, and we should be done with our line, which is going to be called Nervy, here at about the spring of next year. So what this is actually going to be is a shirt, and well, they can just put this on, and there's a single pod that'll clip on the side, and that's it. There's no start button, there's no on, off, something they have to do with it. They just clip it on, put the shirt on. This specific one here, the cardio, we'll be able to collect ECG and impedance, ICG. So the things I talked about with sympathetic, parasympathetic, the respiration, all that will be done by the shirt. So this is certainly something they can take home with them. When they're done with it, for the day, let's say it has a 12-hour runtime. So if you needed to do a 24-hour recording, they can just swap those when they're taking a shower or whatever you need to do at that point. when they put it back onto the docking station, it'll automatically upload all the data to a secure cloud location of your choosing, and it's charging the information, and that's it. So it's really minimal of what they have to do. Essentially, just clipping it off. Machine washable up to 50 different cycles, things like that. So pretty exciting here. And then we can actually see the actual data quality being just as clean as what we saw with the our current mobile system. And yeah, it's actually really nice because they can move around, they can go throughout their day-to-day activities, and we can still collect that information. We're also just the sort of technical specifications on it here. So as I said before, with a 12-hour runtime on the device, the bit resolution is certainly something to pay attention to when we're looking at a system. The mobile device that we have is 24-bit resolution device, and so this will match that. The sampling rate, another thing I talked about, so the 250 hertz being the minimum. This one samples at 1,000. So certainly a nice device if we're actually looking for anything like the ERPs or something. It is sampling at 1 kilohertz. It also has a button here, so we can get feedback from the participants. They can get vibrations, and has a wireless transmission via Bluetooth. So
make a mark on the signal, like a live mark.
Yeah.
Like I'm collecting saliva.
Yeah, absolutely. So you can press it to where the button's cueing them. It'll actually like light up. It makes a sound. You can have it vibrate on them to do that thing, or by pressing it, it can be an event marker as well. Yes. Do you have a question? No. Okay. So anyways, my point was going to be that here. So going through the Nervy cardio is what you saw before, and then the Nervy core, which is going to be a little bit different. That's going to be looking at motion and things like that. So when we're actually collecting data, and even with the mobile device here, posture is extremely important. So if we are, and again, I'm just going to go back to a traditional physiology collection in the lab, paying attention to posture is always important here. So if they're going to be seated for the baseline, there's a task that's seated the baseline, and then we'll use the TSCC, for example. They stand up to give their speech. Those are completely different conditions. We don't want to compare them. So we're going to have them stand, do a standing baseline, and then run through that component. The Nervy core here controls for that different movements that they might be taking throughout the day-to-day. So we can actually compare their change scores throughout the day by using both those different things. What they do is using the Bluetooth connection, they can actually pair with a phone. So for anybody that's doing experience sampling, this is something that we can actually do physiologically-driven surveys. So we can say something like when their heart rate or RSA or pre-ejection period exceeds a certain bounds, send them a survey, ask them what they're doing, and we can design these surveys to be as rich as we need to. So yeah, they are paired with an Android phone. They can last for any sort of specific duration that you'd like to. They'll actually see indicators, so in their current position. So if you wanted to have them, such as like make sure you're sitting, you could actually in real time remotely see that there's an actual their actual posture. So both remotely, and as I said just before, there can be a threshold set that is adjustable by you. That essentially, when they have too much of a posture change or movement, it's going to send a survey asking them essentially what's going on. So even if you weren't looking at the physiological component yet, and you just wanted to get an idea of body movements that is paired with the experience sampling, you can use that Nervy core device along with the phone and the shirt, and then kind of all set up. Yep, and then here's the surveys, sort of the example through our MESA system, which is what this is looking at. So we can, you can certainly design these. It's a very open platform to where any sort of questions that you'd want to do in different ordering, you can do randomizing without, or sort of counterbalancing, all those different kind of things we want to do. And we can do short answer, multiple choice, sort of this sliding scale if we wanted to do some sort of Likert sort of feedback. And all these different kinds of abilities.
Previous like the PSS4 or a Qualms or something to come with through this system.
The
phones there. Yeah, the phones.
Yeah, it's right now it's for a specific Android phone that we would provide with it. It's like $100, but
so it's not. But you could upload a previous a validated survey there.
Oh yeah, absolutely, yeah. It's survey itself, yeah. So you can implement that. It depends on like kind of how it was written, but like most of them it's pretty easy to transform over. So yeah, if you're looking to sort of continue with something, we can ensure that it's working the same way, sending the reports at the same time, stuff like that. It's completely flexible, so it's pretty cool. And then this is one of the last things here is the end-of-day survey. That is pretty cool. So once it's actually done, uploaded and everything, you can actually have them send a survey, which is driven off of that day. So it's not just a sort of scheduled one, but it is what surveys were they sent. Again, that could be physiological-driven ones. And then we're going to count those up. We're going to see what the responses were, and then we're going to feed them a survey based off the results automatically. And then this is actually going to be used in here when we're actually using the Qualtrics integration here. So you would need a Sympathetic system. The server location where the data are being stored can be usually hosted by your IT department, and then we just need the Qualtrics account to get that all running. Cool. Right, so that's it of my formal presentation. We are a little bit early here. There's a lot of time to control for questions. You guys aren't very questioning yet. I also wanted to see if there was time for data acquisition. But at this point here, if anybody wants to open up with any sort of general questions they have or specific or any type, we can go through this. Yes.
I do have a couple like specific questions, and these have to do. I think one of them that I think could be related to data acquisition, but then also just kind of seeing how that looks like on the actual software. I have some examples as well, because that's also like good to look at. But what I've noticed sometimes is that this doesn't happen very often, but and we're using so for our study, we're collecting electrodermal activity and physiography and ECG data, and there's a couple of segments where, and it doesn't happen on every segment, the electrocardiogram doesn't always line up very nicely with the impedance cardiography. And I wanted to know if this isn't having to do with something in terms of like electrode placement, or what could be causing that in that particular segment to not line up nicely, just because it can make it hard for people who are processing the data to be able to line up the electrocardiogram and see kind of what's the corresponding DC-DT peak when cleaning and making sure that we're getting rid of those like movement artifacts.
Yeah. So there's a couple things. So one is ensuring that you have the ground sensor or ground sensor here correctly put on, and that's making good connections with that. After that, which you're probably doing correctly, there is a detrend button on the calibration. It's like the second tab in the impedance application. At the bottom there, if you click that detrend, essentially what you're seeing is a DC off shift or a direct current off shift, which can occur with the impedance signal that we're putting through. So what you're probably seeing is like the blue essentially like being lower or higher than ECG, and you can't look. That should correct for that if you just click that button.
Okay.
Yeah.
I'm opening up the program.
Yeah, sure. Go ahead. Yeah, absolutely.
And if anybody has any other questions, I'll look that up.
Michael, I wanted to ask a question on if you wanted to collect a value of sympathetic dominance, right? So relative awareness if there is a dominance, what would be a measure of that? What kind of data?
What kind of data? Like a hardware you're looking at, or like a statistic output?
Output, like HRV is an indicator of parasympathetic.
Yeah.
Right? And you said that ECG is not enough to give indication of the sympathetic factor. So if I want to look at the balance, if there's a sympathetic dominance.
Yeah. So the impedance cardiography that I've been talking about, that would be the 1A that I would choose if you're doing ECG for parasympathetic. There is something that I would recommend looking into, which is called CAP-CAR. It's a cardiac autonomic balance and cardiac autonomic reactivity. So what that's looking at essentially is the relationship between RSA and pre-ejection period, PEP. And you can see through there like the different like sort of correlations between the two, and seeing like within what quadrant they fall in, and looking at that sort of allostatic load essentially is what you're looking for in there. So CAP-CAR is where I would start with that. But yeah, impedance cardiography is certainly.
You talked about collecting respiratory data to analyze the RSA.
Yeah.
but I mean, so one measure is to do the impedance cardiography. And is there any other ways that you recommend that we can connect with the respiratory signal if we don't want to do the impedance?
To get sympathetic side of things, if you don't want impedance, skin conductance is a thing and maybe the most ubiquitous out there to get the sympathetic side of things. But
Right.
yeah,
So we are doing that, but
Mhm.
if you want to use the ECG data along with the respiratory data, so what are the ways we can collect the respiratory?
the respiration data. Oh yeah, respiration belt is another option. So I have one over here somewhere. I don't know where to put it. Here. So. Okay, so yeah, essentially there's these respiration belts. This one's a sleepmate. What they'll do is actually go around the person, the chest here. These two put into those sides, and then we're actually measuring how much their chest is expanding, contracting when they breathe. Again, sort of the thing that I talked about before is one of the downsides of this. Well, there's a few I can go through, but one is that they're gonna feel that it's like this tight band. Essentially, it's tight to where you can barely put two fingers under it. So for certain populations, that's gonna, be a big issue. They're not gonna feel that, and they're gonna move it around a little bit. Every time there's a postural change, the belt can shift a little bit. It's also a little ambiguous as to where to put it when there's only one. So the idea is that we put it at the point of max exhalation. That's different for everybody. So some people are belly breathers, mid breathers, chest breathers, and so then you have your experimenter that's like passively looking, because if you ask someone to breathe normally, it's the last thing they're gonna do. And so you're having them see like, oh, where's their max point, and then you're moving it around. And yeah, I think the biggest thing that was attention is because at some level during your protocol, the electrodes that we're putting on, come on the clothes, by baseline, they're usually desensitized to them. They can't really feel it there. But the respiration belt's this thick, tight band around their chest that at some level, whenever you're running through their protocol, they're paying attention to the band in their chest. So for that reason, normally impedance, I prefer quite a bit over that, but this would be another option here. Another choice you can do is called impedance tomography, which is actually looking at, you can actually just look electrically between the sort of stress sensors between two ECG signals. UFI makes a tomography device that can collect the ECG signal and then getting that respiration via that method as well.
And this one will synchronize with the the mobile device, or
The belt, or yes, yeah. So with our mobile device, there's a couple different ports on the bottom of this, and well, we can go through this certainly a lot tomorrow, but there's two bio channels. So with one you can collect, a lot of different things. One is ECG and bio one, and bio two you just plug this respiration belt right into it. Yeah. So cool. Yes.
This one might be weird, so we can ignore it if it's better further in the day, but I've had wonderful experiences collecting EDA when I'm in the lab, and it's a baseline task of this very minimal movement. And then I've had a really rough time editing EDA collected in the field, where it's admittedly not collected under ideal circumstances. We're dealing with a lot of noise, artifacts, movement, we're collecting on the feed. And I've struggled to find resources to guide research assistants in how do you determine when it's noise or movement versus someone who's having like a really high sympathetic response, and that's what's kind of like triggering all those SCRs. And I don't know if there's an answer to that, but I guess what guidance or resources does MindWare have for in the field data collection when you don't have videos of movement, when you don't have information about what's going on, and you're really trying to save the data and not just be like, oh, it's bad.
Sure. Yeah. So a couple different. So you said you're taking that from the feet.
Yeah, it was toddlers collected. This was a study we were doing in Jordan. So it was home with Jordanian moms, Syrian refugees. So there's a lot of stuff going on. So yeah, collected from feet. From hands.
Yeah. So yeah, you're certainly gonna have a lot of. If they're ambulatory or not at that age, but yeah, you're gonna have a lot of motion artifacts certainly when you're in the field. Skin conductance is just one of the sort of downfalls of it. So couple different things you can do. So are you looking to report like skin conductance levels or the actual SCR?
At this point, we're just interested in SEL. I don't trust the SCRs because I
Right,
just don't
right.
know if it's movement or
Right.
a valid response.
Mhm. And so in that, if you're looking at just the level changes, is that you're having like dropouts or is it just like a lot of,
So it's like, I can show you some of the
Yeah.
data later. I can pull it up from Paul's lab, but there's instances where it's paired the electrode lost connection because it goes to zero. It's like,
Mhm.
okay, lost connection or something moved. And then there's times where it just looks like a big kind of amplitude swing, and I don't know if that's a valid response or interference because they moved their foot or they got too close to other equipment. I don't know if anyone's worked with EDA.
Yeah, no, I know what you're
It
talking about,
looks
yeah.
like- For some of them, it almost looks like a string of Christmas lights. Like it's so colorful. There's like, oh, so many SCR,
Right.
just up, down, up, down, up, down. You don't really see like the expected slow kind
Uh-huh.
of way.
Yeah, so that's usually indicative of like, so motion artifact normally looks different than just an SCR because it's just more jagged. There's
Yeah,
it's not
yeah.
that sort of slow architecture or sorry, slow moving sort of rolling hills, if you will.
Yeah.
Um,
With some, but it's, and then others, it's way more
right,
up, down, up, down.
right. So do you have respiration data from those?
No
Okay.
respiration
All right,
data.
that makes it a little bit more difficult.
It's really not ideal.
Yeah, no, I understand. Like, I'm somewhat familiar with that Jordan study.
Yeah.
Though. Yeah. So, one thing is if you wanted to look at skin conductance level, like, is it statistically important? Like within a segment, like if you even look at like the change from the beginning to end of it, like, does it really matter that much? Because usually it's unless there's a really dramatic change within there, it's pretty stable.
Well, so I guess that's where I'm struggling, where if we actually have stopped even considering using the EDA data because like if we're editing based off removing what we think is noise, then we're getting a dramatic change in the SEL
Mhm.
compared to this is just what the mean SEL would be without removing any data, without removing any SCRs. And I've been hesitant to use it in any analyses because I don't trust anymore if this is like a valid measure of SEL, or am I just measuring movement and noise and
Right.
other artifacts? Yeah.
Right. Okay. Yeah. So two things I can think of. So one of the within the analysis, there's a block size, and so the second part of the day is like for this. So like,
Okay.
not to say we can't answer this now, but like I will show you exactly what
Great.
I'm talking about. But block size essentially is kind of like a rolling window, if you will. And so what it's going to do is it's actually going to, you can say like how many data points you want within that block. And then what it's going to do is it's kind of the 2 points. So like physiologically plausible, points. So if there's like, we're at say like 5 microsiemens, and all of a sudden it jumps up to like 12 or something really quickly. It doesn't make any sense. So that block size will automatically attenuate that sort of sharp changes, and it'll do it in a standard way throughout your data. So then it's all relative to your study, right? So if we do that with the correct block size moving through, then we won't see 1,000, SCRs anymore.
Yeah.
You really get only the biggest ones, and the architecture will change a lot as well.
Okay.
So you won't see like a lot of them. You'll see like 3 big ones that'll look nice, smooth, and you should be able to discern that very easily from motion artifact. So maybe you could even do SCRs in that case. Maybe not, but at the very least.
If you say maybe, you'll get really excited. But
Right. It depends. So we can certainly take a look at your data. I don't know if you can produce that today, but if not tomorrow.
again,
And kind of go from there. But I think increasing the block size. We normally recommend starting with the sampling rate, but you can go higher. So I could probably recommend like a specific treatment for your data if I just took a quick look at it. But that might be the easiest approach because you've already collected a lot of the data, right? So
the data, the quality of the data is what it is. It's a matter of, is it salvageable or is it just you can't collect this data in the field. It's a difficult situation.
Right.
Here's the things that you should consider going forward.
okay, yeah, let's take a look at it. If you can, we can kind of go from there. But I think the block size next to your problem.
You're having some other things too.
Yes.
Right?
I was gonna say that, and then also just with like teenage participants, even in the lab, it's just like hard because they age it a lot, and then with the TSSC they get extremely nervous. So clearly the stressor is effective here, but that can make it difficult in terms of making poor electrode contact. So
Sure.
maybe we can talk about some like data acquisition tips in terms of kind of like helping just when participants are like extremely sweaty like that. But I have a lot of really similar questions to what Lindsay's talking about, which we can definitely talk about later today. But I actually have like some pictures, as well as like I'm remotely connected to one of our lab computers.
Okay.
So to hopefully make it easier to like show some examples.
Yeah, that'd be great if you guys could. I mean, that'd be perfect. Yeah, so as far as it's gone completely. You were just saying about that.
Was it the data acquisition?
Oh yeah. Yeah, so we're gonna go through that like comprehensively tomorrow as well. So like when we actually put that on different tips. One thing though is, you know, if this is, are you like continuing a study, or is it a point in which we could change something about the data collection?
I think, well, we're still doing data collection, you know. I think I guess it depends on sort of the changes.
Okay. Yeah, so I mean different sites are an option. Like if I think at this point it probably wouldn't be a good idea just because you've already collected some data.
Yeah.
But other options, like if they're using their hands a lot, the wrist is another location. So there is some of the pocket sweat glands there, but it's very minimal. So as long as we control for temperature within the room, which is a good idea either way, that's a nice location. Another one is the shoulder. I think about that as well. That's usually pretty stable. But as far as the data you've already collected and continuing that, we probably want to keep the center. So, but yeah, let's take a look at it and we can go from there for sure. That'd be great. Cool. Anything else? Any other questions? Rachel? Nothing?
No, I don't know.
Quiet now.
I have a lot on brain think about, because when our subjects come in, the fasting is an issue and dehydration is an issue a lot, especially if we try to have the subjects or the electrodes for longer parts of the day. You know, the current study, we do little chunks. We're not wearing them all day anymore. It's a round task that I'm replacing.
Yeah.
Because it's.
Yeah, the fasting is really difficult for you guys.
Yeah, so the fasting is a big issue and it causes a lot of, it comes out in the data, but it's not. You know, I'm going to look at the response to their meal, but the fasting causes it to look different. And it's like hard to get with like a baseline fasting, I guess.
Yeah, you guys are completely out there, different than.
Yeah.
The dehydration component though, is that on purpose or is it just?
No, well, I think it's just when you ask subjects to fast, they tend to be dehydrated. Because I think most of the population is dehydrated, right? And so try to get people to drink enough water. That affects our blood draws as well, but often when you ask people to come in fasting, that tends to be a problem. So I'll notice the signal just being crap, and then it gets better as I've gotten like an hour and a half into the day or something like that. And like I'm sitting, get water.
Yeah, it's kind of crazy if you look up like how much water you're supposed to drink.
Yeah,
it's wild. Like,
so if you guys had any like thought about how that affects it, or is there any data that you've seen about that kind of stuff? Dehydration and.
I mean, yeah, as far as the dehydration effects, I mean, like that is 1A. Like if we're looking at specifically skin conductance level and impedance, I mean, all of them certainly, but like skin conductance, I mean, that is you're gonna have really bad results if they're dehydrated. So one of those, like sort of with your email reminder the day before to come in, like remember to drink plenty of water, and you know, don't drink alcohol in excess is really helpful. But like really, they were driving at home, because otherwise your skin conductance data is like maybe not usable. It's also the case with impedance that we can actually see like electrolyte balances as well. So if we have essentially a very high resistance on there, that can actually say that they're like overly hydrated. And the opposite, if there is a lot of resistance, that usually means they're dehydrated because those electrolytes are actually much closer together, so that electrical conductance is easier. So yeah, you can actually look and see usually if someone's dehydrated or not, just the physiological data. But I would just try to, you know, drive that home a little bit more to make sure that they're well hydrated. I mean, it's a little tough to tell people like exactly like how much they should drink, because sometimes people do weird stuff and they add to what they're drinking or something. But yeah, you're gonna have to at some point like make them drink water. Maybe like
it seems that the reminding them excessively helps, you know, but each individual is. That's what each human studies are like that. The other thing I thought about, because we work with an overweight population, is getting that that respiratory peak and stay really clean, I have to, like sometimes when I place my electrode, but then when I have them, so I place it standing up, plug them in, sit them down, get them all cozy, and then that impedance signal will just like,
Right.
and I have to go back and I'll decide I'll move it down a little bit to get a clean signal, but then I feel like that distance between the back and that front electrode are farther than what that the protocol is saying. But that's when I get the cleaner signal. I'm not sure if it's because I'm with overweight population or
Yeah, that'd be my concern affect that quite a bit. Yeah, as long as the biggest thing with the I'll try to put it right, but like maybe here is fine. Okay. Yeah. So this distance here, like when we put them on these points right here, this lower one is sometimes problematic. So women, I mean, if you're wearing a bra, that's like right under it, especially if there's a wire bra. And so moving this down a little bit more, even into this like lower abdominal muscle, and that is okay. You're going to get relatively different blood flow, but like you can, as long as you standardize that.
I can look at that measurement.
Because yeah, you're going to take a tape measure and actually measure the interior distance from here to here, sort of the bottom of this one to the top of that.
Well, as long as that's solid, even if that back was down a little bit farther, like
Right.
it's an inch and a half below the negative, but it's like 2.5 below.
So, but you keep moving, like this one in relation to moving this one lower, you just move that one lower, right?
Right.
Right.
As
Yeah,
long-
that's perfect.
And that's okay,
Yeah. Mhm.
yeah.
Yeah, I mean, you're going to get some peripheral blood flow the more you go down there, which is like kind of why we want to stop at the xyloid process. But again, as long as we're saying is that between people, you can always, normalize the data and then everything's fine. And explicitly stating like where the electrodes are placed and why they're placed.
And that's part of why my B notch is not always super strong, but because I have the higher my individuals, specifically my injection. So
Right, yeah. And there's a couple different, later today we can look at it a little bit more, but there's a couple different ways we can sort of estimate that B notch. We have the where to be in DCT calculation, but there's also like max slope change and all these different things. So potentially looking at with actual data, like we can see a little bit more, but seeing the B notch like this, the one I'll really mostly use would be, I mean that is controls for like age, gender, weight, race, and all those different kind of things, and it's been shown to be more accurate than a trained coder actually placing that where the B notch is. So that shouldn't be too problematic by moving it down, but you're absolutely going to
because
lose.
like sometimes when I'm training the interns to do it, I often don't mess with the B notch because your algorithms do a better job placing it if you don't see it.
Mm-hmm.
Because sometimes we get like barely anything happening right there in that on that upslope. So it's like where the program is placed the B notch is better than trying to go and think.
Absolutely, yeah. And if you do both, there's algorithms,
Yeah.
right? There's a little visual inspection and the algorithm. One thing that you might want to look to is band electrodes. Is that possible, or would that be too invasive?
Talk about it.
Yeah, I think that
talked about it
would help you with hydration and change of BMI because essentially that has like a center array around the entire band. And then if you were to have movements, let's say from like, a belly shift or something like that, you would still get a lot of different electrodes that didn't have that motion artifact and they would have that good conductance. So it's a lot more invasive for the participant, but you guys are already on some crazier stuff. So maybe band electrodes would be a way to, we have the electrode tape on our store and then you can buy it from us, but it's on there if you want to know what it looks like, Any other questions for now? Or launching? Yes.
I mean, I think it's related to a lot of what you were just talking about. So I think the first thing that I wanted to know is just like this is the first time I'm hearing about the role of kind of water intake impacting signals like, for example, IMP. Can you talk a little bit more about like, what's going on and why that's impacting signal? And maybe,
Sure. Might want to just open the analysis a little bit later on. But so essentially here with this signal, what we can see is that when if they're well hydrated, then we have a balance of that water and the actual electrolytes within their body, right? And so when they're dehydrated, that water is being removed, those electrolytes are much closer to each other. And so then we don't have much resistance on that electrical circuit, if you will, because it's easier for that electrical vector to go through and conduct through that sensor. So when you're actually seeing that, you can actually see the impedance level. So we don't see that here on X here, but you know, what you want to be between is 5 and 35 ohms. That's your range. And so, and it's OHMS. So, but you want to be between 5 and 35. So when we see something that's usually above 35, then that's indicative of them essentially being dehydrated. And then that lower one is that they're overly hydrated. Is not usually a problem that most people see, but being below that 5 ohms is there. So that range is what you can see there as well. Skin condensance, like comparing the two, like when you're previewing the signal, like skin condensance level, you want to be normally between 2 and 20 microsiemens. Sort of portable range is 0.5 up to 35. Above 35, you're looking at like, probably they put the wrong sensor on, they put the ECG sensor on, or didn't have them wash their hands or something correctly. So something's conducting that more. But you know, it could also be something like hyperhidrosis when there's extremely like, you know, high sweaters. When we see that lower level, that's just indicative of usually dehydration. Like 99% of the time when we see that data, it's because they're dehydrated or the sensors are dried out. It's two things, like almost all the time. So when you're sort of in question about all of the other variables, looking to see, okay, I have low skin condensance level, what is my impedance range? What is the level of that? And then comparing the two, and you can really like sort of triangulate, if you will, their hydration level.
Interesting.
Yeah.
And then just to kind of make sure that that's right. So you said between 5 and 35 ohm.
OHMS, yeah.
Oh,
Yeah, it's just electrical resistance rating. Yes.
Since we have this figure of,
Yes.
you said that the LVET is often a good measure of the SNS, right?
Yes.
But we generally don't have a good idea of where the trough is. Is that because of the noise in the data? And this is a two-pronged question also. What are the different sources of noise of this sort of data, and how do we account for that in the data analysis? If we don't know that?
Sure. Yeah. So as far as your first thing, so this left aortic valve opening up, it's not an intelligent valve, it's just pressure valve. So there's 3 kind of pressure flaps on there, and the actual building up of the blood in the left aortic valve is you know, a very powerful thing. And then so when the pressure inside of the heart is higher than outside, it's a very kind of powerful opening of this valve. So it's a very sharp kind of injection. That's why we can normally see that V notch, is because it's like all of a sudden happening. When it's closing, it's tapered though. It's not like this like all of a sudden shut, right? It's just tapering and closing slowly. So because of that contraction and movement is just not as powerful and can be seen in the signal. It's just more like smoothed out, tapered off, if you will. And so other problems. Another one, it just comes into play with like just, you know, anatomical differences between people. I mean, sometimes you'll have things that present themselves completely differently. Like you have like bicuspid valve syndrome essentially. So 2 of those could be fused together. And in that case is, you know, we can see sometimes the V notch is not visible as well, or it comes into play with like the X where it's just like not visible at all. So your second question, you know, the movement is a thing with this as well with impedance, because it's not just like just the sensors moving on the body, but I mean, it's the organs moving around a little bit and blood flow throughout there. So it is just inherently a little bit difficult when there's like, if you're doing like high activity states or something where they're walking around or running like that, it's just really difficult to do. The tape electrodes, the band electrodes that I talked about before, can help with that quite a bit because, again, like they're taking those different electrode sites from a lot of different points on that actual tape. So what that can do is you get like a much clearer picture. I mean, you're going to have higher ratings on there, which I'll show you a little bit how to normalize, but that can help quite a bit with that as far as actually detecting the B and X. Usually with band electrodes, you see it every time with every person. It's more invasive, of course. You have to put that around their entire chest and their thorax and everything. But if you need it to, if like you're like, we need to see B and we need to see X, and we're going to do something like manual visual inspection, we're going to put these on those troughs, then I would recommend that. But yeah, because of the trade-off of the participant comfort for sure, and natural behavior. But any other questions? Good. Okay. How much time it is? So we're set. Okay. We're done a little bit early. So if anybody doesn't have anything else, then I guess we can take a little bit of a break here. Anybody that has individual data they want to show me and not on Zoom and everything, you can come over and we can look at that before lunch. But then other than that, the food will be here around noon, so we can leave and come back, have lunch, whatever we need to do. So, y'all are free.
Are there any questions you want to ask him now? Okay, so, about
I think I have a question before when we're removing the house, like, question was addressed by how like the brand. So well, our and like it exists the that like the size of the house for that and it hasn't really been
Yeah, so we have it. Hang out in the lab, like, nothing else.
Have you ever had to like either practice or actually
Tired and hung it up.
Yeah, I mean, we've kind of already signed a contract with the different designers there. But essentially the electrodes are.
But if they say nothing's wrong, then yeah.
And so I can actually picture in a little bit, but that's a designer situation. So basically, but we're still working on some different types of different parts. One of the patients are having different sizes of people working out sort of we're looking at like denial and that from getting older, kind of like large stuff like that. So we're still struggling with it. So yeah, I mean we're working it out, but yeah, if you're certainly interested.
Yeah, I would love to, like, if there's any way to get involved or I would be super interested. So, mainly for summer. Yeah, just like introducing myself to you, but also, because it's really interesting. Because like my main challenge right now is big signals, and I wanted to use more than one translation scanners besides like the nerds you guys already do. But yeah, I'm excited to see everything that you plan to show us, and also it's an act for.
Yeah, so I have a. But yeah, I mean. Certainly, I can see kind of the guy and there's something that yeah, I'm very interested.
Yeah,
Jumping over to this field, yeah.
yeah, and it's pretty like I have a bachelor's in industrial and graphic design. I made like my first master's in design, like working with tech. So I'm finding like this. Now I'm studying technology, like the technology part of the wearable. So I have like industrial and graphic design background for like in data, but also building the prototype of the patch and to go through the body. And now I'm trying to incorporate like technology to make something in
What's your really
I mean, I'm open to the life. It's just a different pre-programmed, but I think it would look
In her lab. Yeah, she was, I'm not our lab. Yeah, I work. Yeah, yeah, that's.
All right, we are ready. So my plan here is going to be a little bit more open. There's a sort of distribution of people here that have some basic level understanding to advanced people are using it. So my plan here is to just cover some basics of editing and the application itself, the different calibration settings, why we might want to use those things. If there aren't any questions, then I'll kind of just keep going on. If anybody wants me to drill down a little bit more, then I will certainly do that. And yeah, essentially just going through HRV, we'll go into impedance and then also skin conductance, look through those things. I have some normal data and then some sort of ectopic and messy data that we can look at as well. Also, we have about 2 hours, a little bit over 2 hours here. So if anybody else has some data that they want me to look at, or if you're brave enough to have us shown on the screen or something, we can do that. Or we can just sort of end a little bit early and I can come around to your laptop if you have that prepared. Cool. Any questions or anything before we get started? Awesome. Okay, so I'm gonna go ahead and start with the HRV application. And okay, so I'm gonna make some brief assumptions here that everyone knows how to open it and things like that. I'm not gonna go through every single detail. If there is something that you need to know as far as that level, within our support side and training guides, there's a lot of webinars we've done. There's also a 3-part session on our BioLab software for actually acquiring the data. But again, if you have any other questions like that, you can certainly come over and chat with me offline if you're having any sort of technical issues or difficulties like that as well. So a couple things I wanted to talk about with the events and modes before we get started is just looking a little bit into study design and which analysis mode might be the best for us, just up front before actually just cleaning data. The actual cleaning data component, we're going to look a little bit more in depth into tomorrow. Again, unless you all want me to drill down into it or do some more examples. But anyways, from this approach here, the first thing we can look at is our events and modes. And so in this file right here, what I have is we have a situation in which we have a baseline, we have a task, and then we have recovery. And then, of course, we have task 2, which someone didn't enter correctly, which we can look at as well up here. So one thing we could do is if we had this sort of event-based analysis where these are distinct periods where different things occurred, and we have the timing there, we can sort these into a few different modes. And as far as the events and how they got into it, there's a myriad of different ways that these could be put in. This could be keyboard presses, so actually, having an audio video collection and us hitting one of the function keys to say this is when this event occurred. A little bit less accurate, but certainly one way that you can get it done. Another would be if we had like a sort of stimulus presentation setup where the participant is actually interacting with, like, let's say a computer in some way, using something like SuperLab or ePrime or CyclePy or something like that. You can actually code those programs to send up those markers for us automatically. And yeah, anyways, another way we could do this is if we're using something like eye tracking with Adobe, or we're coding the videos in something like Interact or Observer, we can actually create those events in that software. And then if we go over to our ad here, you can see that you can actually just load either the Toby file, the Nodus, or the Mangold file there. So you can actually use those event codes that we've marked in the behavioral software, if you will. And then when we load those in, we can actually ask research questions based upon that. So if it's something like the Toby, and we're looking at gaze fixation, and we want to know every time that there's a smooth pursuit or something, an area of interest that they're focusing on, and then we want to know the physiological reaction from looking at that area. We're essentially coding those areas of interest in the Toby software and ProLab, there it is. And then we're going to load those events into this into our analysis directly. You had a question?
So this is specifically integrated with this because
a specific Tobii eye tracker, the Tobii one?
Any of them. So there's Tobii glasses, Spectrum. There's all the different ones they have. But in there, your analysis routine is probably to go into their Tobii Pro software. It acquires and analyzes the software does. In that software, it's really agnostic to whatever eye tracker you had from them. Because you're just loading the eye tracking data into it, and then you're creating the event marking
But
within.
not the SRs.
Was that?
But this isn't true for the SRs.
I think we can load those files natively. There's a different way to look at that. So within those, we can actually load text files. So, and I believe you can export those as a text file. So in those cases, we can just add a MindWare event file if you wanted. So in the text file, we have a couple different support articles on our support site that cover this, but essentially what I can do is I can export this to a text file here, and then show you what that looks like. And what you would do is you would take your text file that you have and you can transform it into what this looks like. Okay. So it's just a tab built in a text file, so essentially, but then you would just have the event, its name, and then the time that things occur. And so you can just copy and paste, drop your events in from here. Another strategy, which I would recommend for what you have over there, is you can actually go to our ASCII to MindWare converter right here. So this is just a plain text file that will be exported out from SR. And then this wizard will walk you through and actually look at the text file, where your headers, information, and then it'll create a MindWare file directly from that. Okay, so anyways, going back to these events here, we have this different ways we can load this in afterwards. And then just going through, let's just say we have our events now. We can sort them quite a bit differently looking at these. So one mode that we can look at is time. So we can just say there's the beginning of a session and there's the end. We can actually drag items over to where these boxes lay, and then we can define where that entire session occurs, say from here to here. We can also show the events on the screen. So I'll go ahead and jump into this, and we can see that they're displayed. There's right here. So this is just like when these events occur. So this is better usually for when we're looking at some sort of behavioral analysis. We can load a video in the top right, which will synchronize with the physiology. We can actually hit play, and it'll move through, and we can see something like that. So that might be a marker of some sort of behavioral change that they had that were, coding inside of Interact, some sort of behavioral coding software. It can be an event that occurred in the Tobii analysis for eye tracking, different things like that. It could also be some marker that you all are putting in either live during the session or after, such as like they sneeze, they cough, anything like in that instance. One thing that's very helpful when we're collecting data is also to know any sort of external stimuli that might be exciting their physiology. So if we're collecting data right here and there's a hallway and it becomes loud at some point, or there's a door slam or something, we definitely want to notate that with a key press so that we can see if there's any sort of physiological change from that, because of course we don't want that to be included within software, within the analysis. So time mode does exist. We also have an event mode here, and a lot of these modes are the same for the different applications we're using, so I'm just going to spend a little bit more time here. But anyways, within the event mode, this is nice if we're looking at something, which occurs all the time. So if we are coding some sort of behavior or eye tracking, we can have something like the mother-child interaction. So every time mom looks away from child, we're going to code that, and we bring that in. Well, that could happen 50 times. And so what we can do is we can actually say, okay, show me every instance. Let's just say that is baseline to start, but that's looking away. It'll actually take that, it can filter all of the 50 different iterations of it, and then we can actually go over here. We can say it's a specific event that we want to look at. It would take all 50 instances of that, and then we can look for some sort of effect after it occurs. So this being every event, but it's just showing one. And so we would look for the effect as the post event. Normally, what we'll want to do is split these up into at least 30 or 60-second segments. This is based off of our timing criteria for respiratory sinus arrhythmia, which is saying that we need at least 30 seconds of continuous data. We recommend 60 seconds, just because it gives us a little bit more freedom if there are any sort of artifacts in the data, which I'll show you in a little bit. But anyways, if we were to do something like that, we could look at 30 seconds post an event, and then the pre-event would be our baseline, essentially, for that. So we could look at something like -30 in that case. Cool. Okay, and so what this would do as it is it would show us the entire 60 seconds in a row. What we could do in my example is we would split it at the event. So we would actually say that the pre-event is going to be one analysis window, and the post is going to be another. So I'll show you that right here. So here is the actual event that occurs. We can see that it's highlighted right here. This is 30 seconds before, and this is going to be the same event here, and then 30 seconds afterwards. So one use case of that event load. Another is multi-event. So in this case, this is probably what most of you all are using if you're doing any sort of seamless presentation integration. So what this is going to say that we have all of our events in the file, and we want to go through and have that actually sort and markate our different segments. So for example, if I choose the event source here, I can actually say I want every iteration of baseline start to baseline end. So if we have multiple baselines, it'll look for that and it'll sort them all for us here. And another thing we can do is we can also say I'm going to choose individual events and then drag them over. So the start and end of each one. And so doing this, then we create essentially a template. So if there's the same sort of events that occur for every participant, then what we can do after sorting them once is we can save our configuration. Every participant we load subsequently, and we load that configuration, it'll check your entire event list and ensure that they are all included within this participant's file. If they're not, it's going to come up with an error saying like, hey, these events are missing, you might want to check and include them, or as just as a notification essentially. But yeah, another thing that is unique to the HRV application itself is continuous mode. So a lot of times, there's the regulation of needing at least 30 seconds of continuous data, right? And so a lot of times what comes up is we want to know second by second changes, though. We want to see like how is something evolving within that segment. So this is a way in which you actually look at this in a sort. So I'll go ahead and run this through. What it's going to do is it's going to simply ask for our output section. Now what it's doing is, if you can see on the Y, it's actually sampling the RSA and the change of that in addition to heart rate, respiration rate, all the different statistics we might be interested in. And it's outputting those sample by sample into a text file. I'm going to go ahead and just stop this so we don't have to sit here forever. And then we can kind of take a look at that. So in here, what we can see is that we have all of the statistics or the settings that we had set before, start time, the buffer here being that 30-second window minimum that we needed to collect for RSA, all the different settings we have collected, which I'll cover in a second. And then down here, we can actually see the data plots. And so what this is looking at is every second change, we have a score for something like RSA. But it is working in a 30-second bin. As you saw up here. So what that's doing is essentially the first sample that you see at time 0 is from 0 to 30. That's first sample that we see. The second one here that we see at time 1 is going to be from 1 to 31, and then the second one is 2 to 32. So it's essentially a 30-second window that's moving through the data and giving us that average RSA score in this case, for that section. So if we want to do something like a growth curve analysis, then this would be the way to get done.
You would use 30 instead of 60 for the continuous.
Yeah, usually that's just because that's like the smallest window that we could use. So what we would do first is, and I'm doing this a little bit backwards, but it's kind of hard to explain. But first thing we would do is we would edit the data in this event mode, wherever we choose. So let's just go with time because that makes that easy. So we have our 60-second window. Let's just say we're going to start beginning and end at the end. And so we're actually going to come through and we're going to analyze these data, correct for any sort of artifacts, and then we're going to export our results. Then afterwards, if we had the sort of questions that would be revolving around continuous, we would come back to this screen, continuous, and then run it into those 30-second buffers.
Oh.
Yeah. You only want to do this when you have already cleaned the data set for sure, because it's not going to make any sort of editing interpretations based off of it. Cool. So that was kind of an express version. I know it's super fast, but if there are any questions, let me know. Again, in real time, and I'll kind of go through things a little bit deeper. Yes.
I was really interested in sort of, I got the sense of the event, but the multi-event, I'm still having a little bit of trouble kind of wrapping my head around like how that would be utilized. Could you explain a little bit more
Yeah,
about
sure,
like,
of course.
why you're doing that as opposed to maybe doing the time option?
Right, yeah. So in this case right here, in this example, we have events in the file which are actually the markers of when that event occurred. So the baseline, we have a marker for that at time 30, and then we have the end of the baseline at 150. Hopefully your baselines are 3 to 5 minutes at least, but this is only 2. So anyways, because we have those event markers, we can, and they're going to be a standard amount of time, we can now ensure that we have the same amount of data for every participant. It's 120 seconds for everybody. And that's an important aspect, of course. And so this would allow us to use that and actually create a window that you can see over here on the right, that we actually have just the baseline data. And then we would just come through and we would also say, then the next thing that we're going to look at is this first task. We're going to skip task 2 because let's say that it wasn't necessary, hopefully. And then we would create that. And so now what it's doing is when we go to hit the analyze, it's actually making those segments based off of those. Otherwise, you would have to, manually put the times when these things occur. You can drag them up here and do the analysis, and then do the next segment and keep going, which would be, pretty inefficient. Create a lot of output files. Now, however, if your study is not based upon like different distinct portions, if it's just like we just have a 30-minute discussion, then you can just use time mode, of course. But if there are areas within there that you're interested in, you certainly want to break that up and analyze them separately.
So what would an output file look like for that?
I got you. Yeah. She actually works for MindWare, just that's fine. Okay, so what I'm going to do is I'm going to write these all out, which is helpful in a couple instances and actually helps me lean into something that is helpful as far as looking for any sort of abnormalities in the data, also just time estimation. So if we need to know like how long is this going to take me to edit, because in the real world I have 2 hours before I have to go home or something like that. And so I want to know up front how messy is this file, is it salvageable, and how much time is this going to take me. So anyways, I will show you that in addition to answering your question.
And I noticed, because when you hit analyze, it sent you to a view where you're only seeing 3 segments, and maybe I didn't see that correctly, right?
So there's, 3 segments here, because I have it broken up. Just the base. Incorrectly, didn't click this button to catch it. So right there, you want to break it up to smaller segments within there. Typically, I mean, if this one is, I think it was 120 seconds, you can see there, we don't want to edit usually that much data in a row because you could have some non-stationary system data, essentially. So you usually do want to break it up into smaller segments and then just average those results afterwards statistically.
Yeah.
But yeah, so let me do that correctly. Thanks for catching that. I keep forgetting my path there. Okay, but anyways, going back to what I said, like we could do this up front to essentially see how messy the data are, those different components, and do this. Okay, so then what we're seeing here is at the top you have every event that started, so baseline start, baseline end, and then here's another iteration of it, baseline start, baseline end, because they're in those 60-second segments, so there's 2 of them in this instance. We get our RSA scores, so if we were interested in reporting RSA, that participant, that would just average across for those 2. But again, this is helpful in this case because we can actually see that there's quite a bit of difference in the first segment and the second, so something that we could look at a little bit deeper and then start to come up with reasons as to why that changed. But anyways, that's how we would get those within a segment. And then as far as the thing I was talking about, if we actually go to the editing statistics, we can actually see here that there is an area that's the normal peaks that's been identified, but then there's also, this is not the best example because there aren't any artifacts, but right here we can actually see the number and percent of artifacts that occur. So if you come in here and then all of a sudden it's 50, 60, 70% artifacts, we would know, okay, go look at that section right now, see if this is even, something that we can clean, and that'll inform us as to whether we should start from the beginning. If it's so messy in the beginning that we can't even, use this data, we're having to throw that participant out, then let's not start cleaning from the beginning, and then arrive at that conclusion 2 hours later or something like that.
And so can we go back to the main HRV stats page for that for the output file? Specifically?
Oh, you're talking about this.
The tab.
Sorry.
Yes. So when we're looking at I just want to see, so is the output that we're given here in this scenario, is this output file just for the baseline tests, or is it creating an output also for the other tests, like task 1?
Yeah, they're right here.
Got it.
So it's just moving over in the different columns. Again, it's breaking it up into what I chose as 60-second segments. So you're just going to have those until it's done.
Okay.
Mhm.
Got it. Got it.
And then if anybody was interested in looking at biosynchrony between 2 people, this is usually the way that it's done on the EKG signal and the INVI output. We can actually get the the Nervy interval, the time between beats. And so we can actually look at these, and there is a little bit of editing you're going to have to make, such as like the first beats of some cases be sort of incorrect with the amount of time between them because there's not like a beat afterwards. But usually people will exclude those first and last samples, and then we can actually just look at the time between them and compare it from parent to child, and then that would be it. So. Any other questions on the output for now? Okay. I will be going through this a little bit slower tomorrow during that session for those of you going to be here, because that's really geared more towards the basic level of everything. So if there is anything I'm, glossing over and you're just a little bit too shy or whatever to ask a question right now, then just don't worry, we're gonna do it again tomorrow.
If you have a task that sometimes, that's not consistent between participants, like consuming a meal,
Mm-hmm.
and one person it took 45 seconds, and somebody else took 4 minutes.
Mm-hmm.
And I'm just taking like the average of the entire task, regardless of how long it takes them to consume. Is that kind of how you would, you know what I mean?
Yeah, I mean, that's going to be probably your best
Yeah.
bet on that case. I mean, like, normally when we're doing, between subject analysis, you want like about the same amount of data points. From everything you said right there, I mean, I would just try to stay within that range of, 5 minutes.
Yeah, I started saying.
Compare with everything within that.
5 minutes.
Yeah.
I'm trying to make yourself feel pleasure.
Right.
But consume it as quickly as comfortably possible. But there will be people that like just impressively drank the whole breakfast shake in a minute. And then most people are about 3 minutes, 4 minutes. But there'll be like 3 subjects in the 40 that did it in 45 seconds.
Yeah, I think that's perfectly fine. It's just, when we're getting into the point of where we have 30 seconds, we're trying to compare to 30 minutes or something. That's
okay.
it's quite a bit skewed of,
long as you're.
the relationship between the two. I would try to keep within like 5 minutes or something, as far as, and that could be with any condition, not just yours, right? If we have something like an open discussion between a romantic couple or something like that, you can't say like, okay, you have 29 seconds, to wrap this up or something. There's gonna be a little bit of drift there. The standardized, like usually within 5 minutes is our recommendation. Cool. So then, assuming that we have the sort of events and modes component figured out, just want to go into some calibration settings. When I actually go to the analysis, I'm going to go over some more rules of the actual HRV, such as the 30 seconds, that we can go over. I also have slides that'll be shown tomorrow, which go over this kind of one by one that were actually shown in some webinars I just did. So it's just, if you watch those, it's just me talking constantly, so you're probably sick of that. But I'll be going through some of those slides and actually show those rules and how that changes the data and everything like that. But for now, we're just going to go through and I'll just do sort of the questions you have on that end. But okay, so within the HRV calibration settings, we have the calculation method that you see available here. So essentially what this is doing is breaking it down into smaller segments within our window. So if we define them here, we're saying, here's the baseline from 30 seconds to 150 seconds. But I have a question about like second by second heart rate changes, right? We don't just want the heart rate the entire time. So one thing we can do is we can actually turn this calculation method to intervals of 1 second. And we got a lot of great lines, of course, on here, but what we're going to see now is over in the HRV stats, we actually get the mean heart rate and the average Nervy interval for each second within this area. You'll notice at the beginning and end, there are some points at which we're not using this data. There is a, if you actually can hit something that's very helpful within the software, is if we have a question about anything within analysis, we can actually hit Control H. Okay, well, of course, I'm getting an array on this case, but I think how that work, I'm sure. Okay, I don't know exactly what it's saying, but in normal circumstance, every case for the my life before this point, hover over something and you have a question about it, hit Control H. It'll actually take you to the manual for the version of the software, and it'll put to the part of the manual that will cover what your mouse is hovered over. Oh, so just so you guys are aware of that, it normally works. I don't know what's going on with that 404, but something that can help you out quite a bit with that. Anyways, if you do that over the calculation method, it'll take you to an area which actually goes over, it's called a gram weighted period for the heart rate. And essentially, because we need to look outside of the last interval, we can't just use the entire 60 seconds because we don't know what happened before or after that. So that's kind of why it looks a little bit different there. But anyways, yeah, something we can use to get some basic, heart rate and Nervy interval statistics within the actual segment that you identified. Okay, from here, the main component that I think we need to focus on is just probably what most of us are here after, which is RSA. And so there's a couple different ways that we can look at these data. So I'm going to actually jump to the analysis screen real quickly to walk us through these data set, and then I'll kind of jump back to this. So first we have our ECG data. We're going to identify the peaks, the art peaks, and that's the most kind of crucial point for us because we're just identifying some sort of fiducial marker, like when did this occur, this beat, and then when did the next beat occur. So really it's just timing that we're mostly interested in, not the amplitude. That's really not of any interest of us in this realm. Once we've done that, we create an IBI series chart, so the Nervy interval, the time between those beats. So you can actually see in the Y there, it is milliseconds, so the time between them. How we would interpret this is that if it's going down, there's less time in between the interval. If it's going up, it's increasing the time, so there's more. So you can actually see in some of these cases where it's a little bit more clear here that we have a very large gap between these two, that the time's actually increasing up there. But we don't really need to make any sort of interpretations from the IBI series chart, just I'm showing you that that occurs. And then again, tomorrow I'll show you a little bit more on how that can be helpful. But after this, then we're going to detrend, interpolate the data so that everything, as you can see here in the heart period time series, so that there's not any sort of these jagged changes that are going to be introduced into the Fourier transform. So once we've done that, resample the data, We have the heart period time series, or the time between those cardiac cycles. We're going to take these data, and then we can just imagine this line is the Fourier transform, and then it's going to spit out our frequency power spectrum. So when I was talking about before about why we can't use just like heart rates or something to determine the entire autonomic balance, is because in these lower frequency spectrums, this is a very low, essentially between these two blue lines that you see here. And then right here, there's a white line underlaid under it. But of course, this is the lower frequency spectrum. And then this right here is the high frequency spectrum. So in adults, it's 0.12 to 0.4 hertz. And that is the range at which there's just parasympathetic contributions to the heart rate. So anything below that, and again, this is adults, this sort of power area, this can be sympathetic or parasympathetic contributions, and we don't know how much of each, because both of those subdivisions of the AMS can operate at that speed, essentially. But as we go to that higher frequency, as I said before, it's essentially just acetylcholine coming from the brain down the sinoatrial node, a very quick process. And so because of that, we know that any activity from this point forward can only be, again, that of the vagus nerve. As far as changing these settings for children, usually there is an article within the training guides that I showed you earlier, which I can also jump to if anyone has questions, but within there, there's actually different recommendations for children. It's 0.24 to 1.04 for most adolescents. There's also a lot of publications out there that will say that you should have different frequency bands depending on more granular age ranges. So like every 3 years, we're going to have different frequency bands. I can appreciate that sort of strategy, and I think that it is valid. The problem then comes into play, though, is that we're trying to compare different groups. If you're using different frequency spectrum for, let's say, 8 to 12-year-olds, and then you have a 13 to 16-year-old range, then you can't really compare the two. So maybe that's fine for you, but just certainly something to consider. But yeah, anyways, so the area essentially under this curve is log transformed and is reported in milliseconds squared as the RSA value. Respiration as well, so this is very important when we're reporting on RSA. So the respiration data, whether we've gathered that derived from the impedance signal or from the respiration belt, is seen here. What we need to do is we need to ensure that they're breathing in a normative range for validating the RSA calculation. You actually don't need respiration data to get the RSA value. It's simply this, that we need to ensure that they're breathing within the same range. So if someone were to be essentially like breathing very, very slow, where we see this tallest peak over here, then that can be changing and modulating RSA in such a way that it's not really valid. So what our goal would be to do is to look and make sure that the tallest peak and the most activity is within the same band that we're looking at for RSA. So the 0.12 to 0.4 hertz in this case. The peak frequency, so just the tallest point is like something up there, and it's going to pick up on that point, and then it's actually going, which this happens to be 0.3222, and then it's going to work backwards based on a 1 minute cycle, and then determine the respiration rate. So it's not what we're coming through here and counting them to see how many there are. We're looking at it in the frequency spectrum and going backwards because it's far more accurate, especially when you have any sort of speaking tasks within the section. You have some of these respirations which are sort of partial in nature. But anyways, that's how that's done. So when we first come to the analysis screen, first thing is to do is to look to make sure that they're breathing normal. Because if they're not, we're going to throw out the segment, edit the ECG. And then after we confirm that they are breathing in that normal range, then we can go through and actually edit the data. I'm not going to do this with this file because it's clean, doesn't really need any edits, but it's nice to explain up front. Okay. Any questions on that? Is that just day to day? Everyone knows this stuff already, or is there something you would like me to go into a little bit deeper, or just wait till tomorrow? Anybody? We're all good? Okay. Yeah, again, going, I guess, back to the calibration settings, as I said. So the 0.12 to 0.4 hertz that we're adjusting is right here. So again, if we had, we were looking at that child data, you can put in the 0.24 to 1.04 if you're going to follow that recommendation. And so doing that, you want to make sure that you also match the upper quadrant of the lower frequency band to match the lower quadrant of the high frequency band. So you want these two to essentially be the same value in these cases so that there's not any sort of missing data between the two. Of course, we might not care too much about these lower frequency bands, but it's also nice to just have this accurate as the output so that later on, if we have a research question, we can just know that that data is correct. As far as these other bands and what we can use them for, so the low frequency band activity in that range, it has correlation to bioreceptor activation. So if we were interested in VR series, they can be correlated to activity in that lower frequency band. And that is the Mayer wave, MAYER, if you're interested in it. The very low frequency spectrum is honestly not studied that much, but it does have some correlation to temperature regulation within the body. But predominantly, yeah, we're looking in this higher frequency band for the RSA calculation. And one thing I would recommend is that if you are having settings such as we're looking at parent-child interaction, this would be our normal recommendation for parents, and then of course we're going to change it for child. So for those two different iterations, I would have different configuration files saved. And then when we are, let's say, loading parent data, we just load the parent configuration, and we don't have to come back to the screen and ensure it's the correct settings every single time. Cool. All right, so then I guess that's kind of it for just looking at this clip file. I'm going to go ahead and load one up that has some ectopic beats, go through some editing, and then we can see if anybody has any questions. Again, I will be doing this again tomorrow, but if we have any sort of advanced questions for today, we can cover that for sure now.
I was wondering if you can do a demo of you loading a file with like one settings versus other settings, because I know that typically that's been like an issue for some research assistants, and like especially when borrowing computers and having people like for one project have one set of settings and have another project for another set of settings. It's just kind of like I've just hammered it onto my RAs to just always check them. But I think that this could help just uploading those changes help kind of make sure that they're like on their just ensure that they're on the right settings. But I've never seen that. I've never done that before, so I wanted to see
the configurations.
Yeah, just kind of like upload that file. Like
yeah, sure. So then I guess I'll just kind of use maybe the same data set, which should be fine. So in here, this is that warning because the file I had loaded previously had events that are missing in this one. So this is that check letting you know that those ones are different essentially. But okay, so in this case, let's say that we just wanted to have the adult settings here. I'll just go ahead and save this configuration as is. And actually, let me do this for you. I will do a little bit more. We'll sort some of these events out. So let's just put a few in here.
Is there a limit to how many different configuration settings you can save?
Yeah.
Great. Thank you.
Got some crazy going on?
We just have, I'm thinking about all the different configurations that we could potentially have in the lab, and this saving that would help the common issue of you just edit this off wrong configuration. Because we would have a lot of different between parent, child, and multiple studies. We have a lot of configurations.
And you can look at on the back end to ensure everyone did everything correctly.
Yeah.
So in the Excel file, you have the settings output. You can see that they loaded the correct one.
Yeah.
You can even have a macro look through 500 different Excel outputs to make sure that they're all the same.
Okay.
Yeah, that's pretty easy. But okay, so anyways, I've sorted. I'm just going to do one more here. And then, so we have the adult settings, 0.1 to 0.4. We've sorted some of these events. I'm going to save the configuration. Okay, and then let's change that over here. For these.
I had some weird things with configuration, say, probably this is my building, but We have usernames for our computers, and when, like one of my interns would log in their username, they couldn't always see the configuration I had saved.
Oh, that might even.
They could see it because it's on your desktop or something like that?
Oh, well, I don't know, that's, because like it's, you're open, it's in MindWare, right, I save the configuration, but then they open it the next day and pull up the configuration, it's like it's not available for them under a different username.
Because the extension has that on top of it. Yeah, are you using the latest, the 3.2 version of our analysis or 3.1, do you know?
I might have to, I'm not sure, I have to
Okay.
look.
I believe that was an issue with 3.1 and that was fixed in that.
It was also part of the calibration I do with the pressure, with the CNAP, because it needs to be calibrated daily. And my calibration configuration wouldn't be saved for the instrument like later that day or the next day.
Okay.
And maybe that'll change with the 3.
Check the version on that
Okay.
because we don't. I think it was saving that like exact extension before,
Yeah.
and if you weren't the person that
And
was
then
doing it, didn't
wouldn't
work.
find- oh,
But it shouldn't be saving that local data.
okay, probably not done.
Yeah. If you're doing some sort of longitudinal study, you're probably having to use the old one though to finish it up, so that could be it. But anyways, okay, so I've changed those settings there, and then I can save configuration here for the child. And then I'm just going to load a completely different file so we can kind of start from the beginning. And we'll go back to that one. Okay, so this is starting fresh, opening that file. We're going to map our channels, of course. And then the next thing we're going to do is open the configuration, start with the adults. And then it's going to, so this was not like a copy of it, like these were not saved and to auto-populate those. It actually looked for the title and time of when those events occurred and pulled it out of that table for us by using that configuration. Now, if your events don't happen at exactly the same millisecond, which they probably don't for between participants, then we can use the event source in this case. And then we can come up here, and I did this before, but we can actually say resting start, resting stop. So every time that happens, so then the time of when it occurs is not important, it's just the title. And then it'll find those and sort them for us automatically so that we don't have to essentially like keep drag and dropping over there.
Do you have to have event markers set up in a configuration, or could the configuration just be for like calibration settings, the artifact settings?
Yes,
You can just
the latter, yes. I'm trying to multitask, I guess, but yeah, you can totally do that, yeah.
Related to different questions.
Yeah. Sorry, it's a little difficult for me to do this because there's like advanced thing and then there's basic and then like some people can make it today, some people can make it tomorrow, so it's a little dodgy for me to do this. I'm trying my best. But anyways, yeah, so we can see that that's sort of the events, and then here's the adult settings, and then we can go ahead and just load the configuration for the child. And then it's changed the RC for us automatically. And it's removed those, that's because I removed them before, so. Yeah, so yeah, getting sort of the discipline of making sure they load the correct configuration file is one thing, but one thing I like to do is, so if you're having both of the sessions are like within the same file, right? There's like two people at once, or is it child data collection and then parent, or is it, what's the?
Well, right, for this, I'm asking because we have multiple different like projects going on. One of which is just like adolescent data for one of our labs, and then we're going to be working with like a adult data on that same like computer, right? And then for Dr. Hastings' labs, there's just like a lot of like, different international projects and just
Okay.
so not necessarily that we're looking at, and well, I guess one of them is like I'm working with mother and infant data as well. So, and for them, it's super important that we keep those values different because their heart rate is different. So, it's just something that we've noticed in the past, like through processing data, because we're working with so many other people's settings because of all the other projects. And then, everybody sharing those like lab computers and reserving them during different times. It's just, we're trying to figure out ways to sort of create multiple safety nets, because I think either way, like they should still be making sure that the settings are correct, right, regardless, right? In case, you know, there's maybe like a software glitch or something going on in that computer for some reason, like, but I guess that is just my question, is just kind of like what other safeguards can we put in place to sort of make sure that there's like less human error when editing, right? So, and yeah, and the settings tab is something that I use, and I think right now, for my projects, I also have like a script that checks to make sure that those
Right.
are good, you know. But it's just the sooner we can catch it, the better.
Yeah,
If
yeah,
we
absolutely.
can avoid it, like, because if we created an output file, then that means that Ari is gonna have to schedule another shift and create another output file the next time they go, you know. So it's just sometimes like trying to save time while keeping accuracy, you know. So those are sort of things that.
Right, sure. There is a software that we are releasing this month. It's a study compiler. We had it before a very long time ago, and then Windows kind of broke it for us, but then we have created a new one. So what that allows you to do, and it's much cheaper than the rest of our analysis, but what it lets you do is define all the different information like demographic, the collection, like all the different criteria, such as like the respiration bands, everything for all your data, all your output files. If there's like 5,000 of them, it'll just point you to that folder. It'll take all of those, and then you can start to say like, ensure that these all have the same settings. It'll just check it for you automatically. So that's something you can do. Again, it's on the back end, but something that could be really helpful for looking at those things before you go any further. But as far as, you know, just catching up front, well, I asked that one question about the different populations there is, if you have the child data, like having a folder for them and having that configuration right in there, so that when they go to load the data for the children, like the configuration report is like in that folder, right? So then there's not like any ambiguity as to like which one they should use.
That makes sense.
Yeah.
Yeah. So, yeah. I mean, that's typically how we're storing data right now for that study, is just kind of keeping parent and child data separately to begin with. So it's not like they're processing those in the same sitting just to avoid those issues to begin with also. But just keeping it in sort of like the main folder so that it's easy to find and just apply to all of the.
Right.
Yeah.
Right.
Okay.
All right. So I'll go ahead and, yeah, I guess I did load this. I don't know where I'm at, but. Okay, so what we can see here when we first go to the file is we have our blue circles essentially identifying that those are good R peaks due to the timing criteria and the various algorithms that we have in play to look for the beats, such as the energy envelope, cycle timing, and things like that. And then when we do see an abnormality and that is identified as a yellow circle, letting us know that we should look closer at it. Doesn't mean that it has to be made, but it is certainly something notable in this case. And so yeah, what we want to do is we can go and edit ours, and we can look this a little bit closer. And one thing I like to just remind people of is that let me change color a little bit. So if we actually look here at the artifact, we could be maybe inclined to jump right to that section and start editing data. But what I would recommend doing is looking first at this higher level and saying like, okay, once we looked in, it looks like somewhat of an abnormal beat. Let's go look at the rest of the file and see if this is something that's repeating for them, or if this is just an isolated event that they had one sort of like, like one premature atrial contraction essentially. But did that happen multiple times? And does it get worse as things go on? Because if this occurs too many times, then we just can't use that data file, of course. So something to consider, and just do a little bit of spot checking to see if this is something that continues to occur. And then we can see here in this case that there is some additional abnormality in the data, which is picking up on that is not due to motion artifacts. So something to just kind of take note of and look through this to see sort of how bad it is. Of course, there's also that check. I showed you writing all the segments out. that we could look at it from that level. But this is really nice to see as a visual to differentiate an ectopic beat potentially from a motion artifact. But also when we're going into this, another thing to look at is not just jumping within the segment to the issue, because when I see anything abnormal like this, I would, start from the beginning always, because there could be something like an error that the software is making. And there also could be a beat that occurs just at the right time at the right energy envelope, and we marked it as good, but it is actually, in fact, something we want to look at closer. So I usually do about a 10-second window by clicking on this window here, and kind of starting from the beginning and just taking a visual inspection to make sure that the blue circles are on actual peaks, and then just moving through the data set until we arrive at that actual ectopic location. Okay, so I'm going to turn off respiration for now. And so what we can see here, there's a couple different features here that, again, I will show in a little bit more detail tomorrow, but we have the P wave, the Q, R, S, and T that I talked about before. So the P wave being the atrial depolarization, preparing for the larger contraction. And so in some cases, what we can see is that it's actually missing. And there's sometimes a combination of different premature contractions that can occur. So it's not like if we see a PC, that's all it is. Like sometimes we can see a premature atrial contraction, but then there's also like an issue with the Purkinje electrical conductance fibers. So we also see a PJC as well. So it's not really that important that we identify these in this case. It's just that we want to see that this is abnormal and that we need to make an edit based upon that. I would not recommend, screenshotting this, putting this into a manual and saying, when you see this, do that. It's more about knowing what a normal average ECG looks like, QRS complex, I'm sorry, and then comparing that to something that looks quite a bit different. So I said before that the amplitude is not really that important to us, but in this case, it is notable, right? It is lower than the rest of these, which is one identifying mark. And then, of course, the P wave is missing in this case. And if this is the T wave, it's quite distorted. I think this is more likely some sort of compensatory cause because this beat is early. So when that occurs, it's something like you can think of like a refractory period, so that essentially there's a period in which the synovial node can't fire again. It's sort of resetting that rhythm, if you will. So I think this was occurring here. And so anyways, long story short, this is an abnormal beat because of those different things. So what our job would be to do is to remove that. So what we can do is we can click the delete button and actually remove that abnormality there. And then what we're going to do is we're going to implement what's called a mid-beat procedure. So in this case, we're going to try to continue our series of data and with sort of minimal disruption and skewing the data as minimal as possible. So what this is going to do is we're actually going to put one of these cursors in the interval before and after that event occurs. So again, we're going to PQRST, PQRST, make sure those are good, and then on the other side as well. When we do put them in that surrounding intervals, then the mid-beat function will light up. It'll say that based upon the average distribution, so the average IBI for this entire segment, that one beat is missing within those, and then we can essentially place that mid-beat there. It's going to put it at 0 amplitude because we're not trying to guess at what amplitude it was. It's more about just simply the timing, and that would be the edit for the section. And another thing is just like before, looking at the entire segment from the beginning. We also want to do the same thing and make sure that we're looking at everything to the end of it once we're done. Okay, so once we've done that, we can see that we have now a blue circle with the orange crosshairs, so another symbol that we have available. And this is a good time to talk about the rules of sort of HRV editing and what we want to standardize to. One is that we have the called 30-second rule again, so that is that we need 30 seconds of continuous data. And again, that is in relation to a certain amount of data points based off of respiratory cycles. So what we need to do here, actually, I'll save it. That file. So right here. So as far as the respiration rate setting, so we have defined our RSA band up here, and then this button is saying that, okay, base that RSA band, make the respiration band the same as that RSA band. So what it's doing is actually based on 1 minute cycle again. So if we actually took 0.24 and multiplied by 60, you're gonna get 14.4. The same with this, you're gonna get that 62.4. So that's the range of that expected respiration, which they're allowed to be within, if we're going to be looking at that RSA range. And so, yeah, anyways, that's kind of a keynote there that we want to look at. And so within that 30-second range, we need to make sure that they have at least, I don't even remember what it was, but it's 0.72 for adults, but okay, 14.4. So 14.4 is the minimum amount of respirations that can occur within here. So if we actually turn this back on, and we can actually see all those respiratory cycles there, so they're over 14, it looks like. This is, of course, adult data that we're using, but they are at 16, so they're just above that. But of course, this is adult breathing. And so one of the problems is if we start to get less than 30 seconds, or I'm sorry, less than 60, is we can start to remove data here. So let's just say that we're like, okay, well, this all is invalid because it's motion artifact. It's actually fine in reality, but let's just, for sake of this argument, say that that's true. Now, when we start to look at these data here, we've actually removed 4 respiratory cycles from that segment. So something to be aware of when we're moving too much data. And this is really only the most important thing when we think about the mid beats, because when we actually delete peaks, it is now calculated from the first and last beats. So from here to here, which is fine. So it's going to change that minimum recommendation for the respiration. That's fine. But the mid beat is the problem with all this. So while we do need 30 seconds continuous data for that RSA calculation so that we have enough respiratory cycles, if we estimate too many mid beats in a row, we're actually removing the changes in heart rate due to breathing, right? So we're breathing in, heart rate speeding up, we breathe out and it slows down. And so if we actually remove too much of that information, let's say that we actually needed to estimate 4 beats in a row, you can start to see that on average, you've removed all of the effects of entire respiratory phase and its effects on the ECG data. So now we are going to be over or underestimating RSA because we've estimated too many beats in a row. So our recommendation on this case is that you do no more than 3 beats in a row. You can see here, if I move this out, it's actually detecting that 4 have been missed, which seems to be accurate. But again, now that entire respiration has been removed. So if we were at 15, or let's say we were at just at 14.6 or something, and then we do this many beats in a row, well, now we're at something below that, so 13.6, for example. So now this is improper. So trying to keep those mid beats to a maximum of 3 in a row. We have our 30 seconds of continuous data. And then as far as removing data, which you saw me just do, we're going to try to keep at least 60% of the data within a segment. So again, if we were to come in here, we say that the data are very messy in the beginning, they're very messy at the end. I can do Control Shift and actually remove all those data on the wings. And then we essentially need to put our cursors over the first and last points. And then our delta will tell us the absolute time between them. We're at 35 seconds, so we actually have enough data for this segment. Yeah, and anyways, looking at that, another thing that we have to look for is the percentage of our estimated beats or our mid beats. So if we actually go to point distribution up here, at the bottom right now, we can see that we have a couple different identifying sections. So the blue being the amount of normal beats, happens to be 92.3% in this case. And then in the middle here, we have 7.7 estimated beats, or those mid beats. So the 4 that we see here constitute 7.7%. We want those estimated beats to be 10% or lower. It's called a 10% rule that we have. Now with child data, and we're looking at 3-year-olds and they're moving around and stuff like that, you may want to, as a research group, change that upper bounds to something like 15-20% is the highest we would ever recommend you do. But yeah, usually if you can keep it 10% or lower, that would be ideal. So 30 seconds continuous data, which we have. We're keeping our estimated beats below 10%. We should have 1 less estimated beat in there, so that we only have 3 in a row. And then we're all set.
So if that was one segment of a 5 minutes rest, and you needed to cut that front and back out, you wouldn't want to still use the segment in the 5 minutes. Like say you wanted an average of the whole 5-minute rest.
Yeah, I would include this.
You would
now
as
there's
long as you have a certain percentage left of this segment.
60%, yeah, and that would follow within the actual condition itself.
Okay.
But there's a little bit of a caveat to that. So if let's say that we're doing a baseline 300 seconds, so that's broken up into 5 60-second segments. We could get rid of 2 of those and still have 3, which would be 60% of the data for the baseline, which should be enough. However, if let's say it's a condition and there's a distinct period within there where there's an event that occurs, and that's like, relying on a dependent variable essentially, you really have to look at it a little bit closer, because if a student's like mid-beating right over this event when it occurs, they're going to remove that effect. Or if they're saying, oh, remove this data, so something like that. So having something like, even if we're in a time domain mode, but showing the events on the screen so that we know when that very important thing occurs, such as like if you're doing a blood draw or something like that, that would be a point where you're like, hey, don't remove this area because we need to know about it. If you have to remove it, throughout the subject. And then also piggybacking off of that, a little bit on a different tangent, is using 30 or 60-second windows. So you'll see in the literature, there's a lot of people use 30 versus 60. So why we recommend 60 sort of as a blanket recommendation is, again, because we can do things like this. We can, if we had 60 and we had very messy data in the beginning and the end, we can remove it. We still have 30 seconds of data. If we look at a 30-second window and there's a problem where we can't mid-beat because it's the first beat of the last beat, or there's just not enough information there, we're all mathematically have less than 30 seconds, so we can't use that segment. But the advantage of using something like a 30-second window is we're focusing our output and our statistics right around a specific group. So if we had something like we're looking at an emotional response that occurs at time 22 seconds into something, and we use a 30-second window, the physiological data and effect is more focused around that. If we use 60 seconds, now you're having effects that are probably having nothing to do or related to that event. So that's kind of the idea and why it's sort of advantageous to use 30 in some cases. But I would recommend, I would hope that you'd have very clean data if you're doing that, or you're going to probably exclude people more often. Yes?
Maybe a very irrelevant question, but I'm still going to ask. This is the first time I'm seeing the software. So is this the raw data, or is there any sort of noise filtering applied to what you're seeing right now?
Yeah, sure. And are you gonna be able to make it tomorrow?
Yeah.
Okay, cool. Perfect. I'll go through this like a lot more, but no, yeah, it's a good one. So no, it's not. It's not quite the raw data. So we have a couple things in here. So there is a baseline and muscle noise filter. I have edited, if you remember more, or previously I had made an edit and I saved the edit file. When that happens, it's grayed out because I've already made a decision.
Okay.
Because that edit loaded, but normally you can adjust these things. So baseline and muscle noise filters is going to remove any sort of general motion artifact, and it's also going to create essentially like a band pass from about 0.5 to 40 hertz. That's where we expect ECG for a human to occur. And then the second one here, notch filter, you can have any sort of electromagnetic interference, so such as like a light. I mean, it could be a power transformer line that can emit this noise. Then this right here would remove that. So in this case, we don't have that, so we have the notch filter off, but the baseline and muscle noise filter is on, so that's going to change a little bit from the raw data.
But if you're, let's say, monitoring someone for the long term, for a day, for example, it's very difficult to go like 30 seconds, 60 seconds, or whatever. Is it possible to filter further for things you are manually editing right now?
Yeah, it's a couple things. Yeah, 2 things I would recommend. So one is I would probably stay away from RSA. There's no way you could edit. If you have 24 hours of recording data, how are you going to look through that much? Like if you have a good sample size, it's almost impossible. Like, and assuming there's a lot of edits within there, how with the actual time and manpower to do that would be tough. So RMSSD is usually what I'd recommend for the very long recordings. RMSSD is a lot less susceptible to any sort of motion or topic beats that might occur. So in those cases, you can really look through for just like egregious changes within the file, like very long artifact periods, and correct those. And then you can kind of, the assumption is the rest of it would be normalized by just looking at that root mean square successive differences.
Yeah.
The second thing though is there's a tool in here that I show you. So with our newest version, you can actually search for the next and previous artifact. So in this case, and you can also see it's the control and right button on the keypad. So I can actually hit this and look through, and it'll search the segment for the next one that has an artifact there. So if you have very long recordings, this can kind of help you jump in, and even if you're doing the RMSSD, you can really quickly come through and see like areas like this. I mean, like let's look at this a little bit closer. There's a lot going on there that we need to correct for, and yeah, something to make it a little bit more digestible. But regardless, I mean, looking at RSA for 24-hour recordings, pretty tough unless your N is like 10 or something, you know. So yeah. Does that answer your question completely, or?
No, I'm getting a
Okay.
better sense
Okay.
of what I'm looking at, but
Yeah.
thank you.
Yeah.
Sorry.
Tomorrow when I start from the beginning, I'll be better for you. Don't worry. But yes.
Right. I'm looking at dyads, and one of our participants who's in a lot of the dyads has frequent PPCs and is in bigeminy some of the time. Is that going to be problematic?
What was the last thing you said?
He's in bigeminy some of the time.
Okay.
Is that going to be problematic in terms of doing PPCs?
Yeah, I mean, the frequency of how often they occur is important, but so something that important to look for with VCs is there a reset in rhythm? Like, is the sinusoidal node able to reset that rhythm afterwards? And if it's not, or if it's just occurring like compounding afterwards, if the latter is happening, like, yeah, it's pretty difficult to use that person. You could try the mid-V function, but again, if it's not correcting that rhythm, then you're just kind of shooting in the dark a little bit, because that mid-V function is based off of the normal IVI timing. And if that's been disrupted because of the actual PPC, then yeah, you inherently have a problem in actually editing those data. Yeah, so I would say like that's on case-by-case case-by-case basis. So if you wanted, one thing I'd recommend is that, I mean, I know you've actually paid for training before, so I'd recommend you schedule a session. We can actually look at those, or if you have it, I can look at it later today or tomorrow, for that, particular
I
person.
don't have it on me right
Okay.
now, and I can have something maybe.
Yeah, tomorrow is fine, or again, we can always do it remotely over Zoom, and then we record those sessions as well, so you have that. But yeah, so it's all kind of about like resetting that rhythm right now, and if that's working.
Okay.
In a lot of cases with PCs, it's not, and it's just like you see them like just continue on for the rest of the file. One thing of note when we are looking at abnormalities such as those ectopic beats is pay attention to the heart rate a little bit. So as the heart rate increases, you're going to see less of those on average, because it's just like essentially like a system working more efficiently. So there's less time for those abnormalities to occur. And whereas when the heart rate drops down, you might see more of them. So something to be, conscientious of when you're looking at the baseline data. Their heart rate's going to on average be slower during that point in time. And so you might see more of those issues there. But it might be the case that later on you see less of them. And so just, yeah, something to kind of be aware of as we look at the data. In a lot of cases, if your baseline data isn't usable, and you can't really use the file in itself, but something to be aware of when you're kind of looking through the data set. Okay, yeah, I have a couple more examples here that we can go through. I can also try to edit some of these if anybody wants to see that, but I think most people are pretty experienced in editing data, so we can do that, or we can jump into impedance and skin conductance. Does anybody have any preference? Okay, let's move on then. Okay, so I have loaded a file into impedance, and you can see a lot of the settings are identical to what we had in HRV. We don't have the continuous mode that is exclusive to heart rate variability, but as far as the different events and modes, those are all identical. As far as calibration settings, we'll spend a little bit of time on this. So one thing up front, if there is anybody that has a continuous blood pressure monitor that we're also using for this, for these sessions, if you have that synchronized with everything, what you can do is your normal analysis routine would actually be, you can edit the HRV and skin conductance whatever you want, but the idea is that you're going to first edit the HRV, then you'll jump to blood pressure data, you'll create an output file for the blood pressure information, and then if we actually check this little thing right here, which is total peripheral resistance or vascular resistance, it'll actually then, if I hit analyze, it'll actually load the blood pressure data And then inserting that, we actually can get the mean arterial pressure, total peripheral resistance, horrible, will actually show up right here. So mean arterial pressure brought in from that output file, and then we'll actually get that TPR reading right there if you're interested in that.
You said you cleaned the heart rate variable, you cleaned the heart rate data and then the blood pressure data, and then you combined the.
So it doesn't, I mean, the heart rate, skin conductance, and blood pressure doesn't really matter, but it all has to, or the blood pressure has to happen, sorry, ECG and the blood pressure data has to happen for impedance, because we need those things all to happen for that, so we can load the actual TPR file.
Okay.
And you know, the HRV editing, like theoretically could be done after impedance, but if we do that, it's a lot of times becoming like a redundant work because yeah, that I was going to show that in just a second here, but essentially, if there is an abnormality in ECG data, we should correct that first in HRV because otherwise we can make the same edits within impedance, but you're going to have to make the exact same edit every single time and then make a mistake. So what we'll normally want to do in the R peak max effect settings, there's an extremely important button here at the bottom, which is ignore estimated beats. So we'll make sure that is checked. And if we were to do something, I'm just going to plunge just a little bit, but let's just say that we had a mid beat that occurred right here. Let's just do that one. And let's see, have a mid beat in there. Okay, so had we done this in HRV, when we first loaded the same file into impedance, you're going to see that estimated beat there. And one thing we want to do is we do want to make sure that we are ignoring those estimated beats, because if we're not sure when the electrical component happens, then we certainly don't want the mechanical blood volume and contractility included as well. So what it's going to do is it's going to essentially not include any information from this point to the next beat. It's also going to exclude any of the blood flow information you see here. But anyways, yeah, normally we want to do that so that those edits that we do in HRV are automatically brought in when we load the file into impedance.
So I could do the BP2 before, and then instead of doing HRV, then impedance, and then my BP. But
And then your VP or something.
yeah, I'm doing my BP third, so I could do the HRV, the BP, and then put them both into the.
Yeah.
Great.
Yeah, I mean, if you're after 12 peripheral resistance and doing it accurately, then
Good to know.
yeah. Okay, so I guess moving on from here, just going back to the calibration settings, and we can actually look at this waveform a little bit closer. That's what that button is. So, if anyone's interested, it's calibration settings important, blah blah blah. Electrodes, so that's what I talked about before. We have the actual spots that we're putting on for these different waveforms. If you are using the band electrodes, as I've brought up a couple times, you can drop this down to band settings. So it's actually looking for the front and back distance. So when we're putting a band on, you know, it's very unlikely that you're going to put that perfectly around their chest, and there's going to be just different parts of their body that are not going to allow that. And so we're actually going to take a measurement between the bands in the front and then between the bands in the back to get that, and then it's going to put those together to get that actual average electrode distance. So just a note, but I think most people are using spot electrodes. Another thing on top of that, though, if we are using band electrodes, stroke volume, so how much blood is actually pumped into the heart each beat. The most sort of common ubiquitous calculation method for that is the Kubitschek stroke volume calculation. But anyways, next to that is the optimize button here. So if you were using spot electrodes, let's say, and you wanted that blood flow information to be in the same range as another study that used band electrodes, this will normalize this data. There's an algorithm TTE here that essentially takes this information and we'll put it in the same range for you. So just if that is of interest to anybody, you can just click that button right there. Okay. So then from here, Ensemble length is something that it could be important to everybody here. So normally we're looking at an ensemble that is somewhere around the 750 milliseconds for that cardiac cycle. Normal BC means somewhere around 1 second. And this is not the file to look at for this. Second.
I did have a question.
Yeah, go ahead.
For, so this is not ideal, but it's happened like once or twice where, let's say we don't get that measurement between the collarbone electrode and then your chest electrode, right? What do you recommend that we do in those situations? Is it better to just not use that file at all, or is there a protocol that we could sort of to maybe hopefully salvage that file?
So you can, so it's a good question. There's, things as far as electrical ejection time and then the pre-ejection period. I mean, those are unaffected by that distance. It's just timing criteria. It's the blood volume information, so stroke volume and cardiac output, that would be invalid because we don't know that distance. So a taller person would have more blood in that region than what a shorter person, so that's why we need to get that measurement. So I would just ensure that you don't use those statistics for those people. A control on that, though, which I think you are interested in, is if we come into the calibration settings here, I would turn that down to 0 for those people that we don't have that information for. Its default is 25, but that might make us think later on that it was actually 25. If we put it at 0 because we don't have that information, then every time we look at those things, it's going to be 0.
Okay, that's very helpful. Yeah, because I know I don't know if there's any literature out there that does something like this too, but we do take like height and weight of our like participants and like hip and waist measures. And so I was wondering if like maybe because our age range are 11 to like 15-year-olds, so their heights are like the 11-year-olds are so tiny and like the 15-year-olds are like so much taller. So I was wondering if I don't know if this is something that you know of, but if there's a way that we could even just estimate just based off of their height.
Yeah, there's quite a bit of literature on it, and we have a way to calculate that actually.
Yeah.
So thanks for that question.
And if that would be better than setting it as 0, or would that still be sort of invalid for stroke volume and cardiac output?
Yeah, if you have those things, then you can change over to this smart Bernstein algorithm, which takes height, weight, and then you can calculate ideal body weight from that.
And would it make sense to switch that for only participants that are missing the electrode?
No, you have to do it for all or not.
Got it.
So, I don't know the exact electrode placement, but it is just the vertical distance that makes difference.
Yeah.
The horizontal,
I mean,
if you're doing it with a band, how are you?
If you're doing
If you're doing it with a band, the horizontal distance.
it's still looking at so there's mentioned 2 bands there. It's just the distance between the 2. Right. Yeah. Yeah. I mean, sort of horizontally.
You come at the back too, right? Don't you?
For impedance, yeah, we put 2 spot electrodes on the back. So you can think of those being the band would circumvent their chest, and those would be on the back. Yeah. So it's one band, and then there's electrode plugins on the back of that for there, and then there's electrode plugins on the front of it for the sensing.
If you are doing a comparison between 2 visits with one person and you do find that your electrode placement was farther apart on one than the other, is that affecting my ability between the 2 visits to compare that subject?
No. I mean, this
it's fine.
electrode distance will control for that.
Okay.
And put it exactly the same range. Yeah. But of note here, one thing to be aware of is when we're measuring these things, we'll look this a little bit closer tomorrow. But we actually want to be sort of following the interior distance between the 2. So actually, I'll just do my buttons. So we can imagine that this is the top sensor and this is the bottom one. It's actually pretty close. So in centimeters, we're going to want to take that measurement. But we want to be at the top of that metal point on that electrode. That is actually where the conductance would occur, the actual metal component on there. I also like to take that because you can feel it when you're putting that on. So once the actual lead is on there, on top of the actual, imagine this is the actual electrode, here's the lead snapping on. It would be the top of that, this one right here, and then the bottom of this one. So it's like the interior measurement of what we're looking for. Not otherwise, I mean, you know, it certainly is relative to what point we're picking, but then it's like a little bit ambiguous. Like one person picks the outside range, one person's in the middle, like you don't know.
So balance distance.
Yeah. I guess it's like a, I don't know, easier way to say that, yeah. Cool. Right. Cool. This, let's see here. Okay, so as part of finding landmarks on peaks, there's a couple different ways we can do this. And we have sort of the more popular ways of finding these different components on these big ones, but we'll go over just for a second the ones that we recommend. So what this is going to do is we're finding the Q point. So on the actual ensemble here, I'll go through this a little bit here. So in the red here, this is actually the average ECG. So it's all of these cardiac cycles combined into one ensemble average. And then the blue here, we have the same thing for the different blood flow cardiac cycles. And so in here, we can see that as an average waveform of all of those combined. And what we need to do is we need to find, if we're looking for a pre-ejection period, let's say that that's our end goal, which is going to be that Q to B location. We need to know where Q occurs. However, the problem is that in a lot of participants, that sort of trough is not available. Sometimes it goes flat straight over and then up, or there's more of a curved point from that baseline up to the R peak. And so the best way in a lot of cases is to look for constant relationship, which has to be about 35 milliseconds from R to Q. It's pretty standard across humans that it is 35 milliseconds. Age can change this though, so in children it's going to be a little bit shorter. So depending on your age range, you certainly can change that setting, and just by changing that constant value right there. Again, there's a lot of different ways we can look at that, such as you know, similar to the high frequency RSA bands and the HRV application. We can take that more granular and we can split the kids into different quadrants based upon their age, and we can do the same thing for the Q point calculation method as well. But this is something to certainly look into if you're looking at your data set and that Q point that is being estimated on the screen is certainly incorrect, such as it is not placing it in that trough. That might be a good indicator that we want to look and see if we want to, you know, sort of customize that Q location based upon our population. So, you know, we certainly can jump into the ensemble editor and we can actually zoom into that area of interest for that Q point. That was a little bit too much. And once I zoom in that direction, I can also go on the x-axis here to make that trough a little bit more pronounced. So it's the lowest point before it goes up, so it's correctly identifying that there. But if we came into our data set and it's just regularly estimating it outside of that range, this would be a good time for us to think about looking at all of our, you know, maybe a sort of random, quasi-random sampling of our data set and seeing where the average Q point is located, or certainly we could reference some sort of common literature recommendation upon that age range.
And this may be a basic question, but how does the body that and how does it affect the impedance data that they're collecting?
It does, yeah. So yeah, it was sort of.
How do you filter that, or how do you take that into account when you're analyzing the data?
So there are a couple different things you can do. You know, it's helpful to really understand, like if you're going to be sampling people with a very high BMI, usually it's like above 40 or higher, in which that actually, those lipid layers actually become an insulator for that electrical signal. And so in those cases, you can use different impedance arrays. So, I mean, you can put it in a lot of different areas. You can actually take two on the sides, which is helpful. So instead of this, we can move it to here, this location. You don't have to do it for everybody, but that is one thing you could do. One thing that we're looking at, for instance, for our shirt is we're actually taking it from the shoulder, because we actually don't see, you know, that much of that, you know, lipid concentration in that area. So something that can be helpful for if we can control for it up front. Another thing is within the devices, especially ours, we can change the drive strength that is creating the actual impedance signal. So right now it's 0.5 milliamps. We can do that to 1 or 2 or something like that, and then that will impede that with the blader a little bit better, and then we can actually see that signal on the other end. But
You change it for everyone or?
yeah, you'd have to. But I mean, you could certainly do it. It's not gonna hurt anybody to do that. So if we knew like, oh, hey, we're sampling like a higher BMI population, let's control for that up front. Let's potentially look at a different array of impedance sensors or actually modify the hardware a little bit.
If you want to do multi-array, can you do that? Does it have enough?
So yeah, you want to be a little bit careful. So this can only do one, but you could get multiple devices. We also have a stationary unit, looks more like an EEG amplifier. In that you can just have different cards instead of all these different things. It's quite a bit cheaper. And so in that sense, you need to be a little like thoughtful about how you're doing it. Of course, I know you would, but you only really want one of the constant current sources, and then you have multiple sensing sources. Yeah, but you can certainly do that. I mean, it's the mobiles are going to be synchronized in a millisecond within our software, so you could certainly do that. But it's just having 4 mobiles around someone is maybe not ideal. So the wired unit is maybe a better application for that. All right. So anyways, there's the kind of viewpoint. I'm just kind of harping on it a little bit because I know a lot of us are looking at child research here, so something to be noted. But anyways, the projection period that we're looking at is based off the Q to V relationship there. And again, the R to Q is a pretty solid constant across most humans, which is about 35 milliseconds. So we're going to identify R, count back 35 milliseconds, and place Q there. It's not looking for the trough. It's looking just based upon that that constant there. Okay, the LVET windowing. So this is a 300 and 600 millisecond offset from the V notch. So if the opening of the left aortic valve occurs here, and then the closing is here, let's set a 300 millisecond offset from V, and then 600 millisecond here. So then what it's looking for essentially is the lowest points within this range. And so the idea here is that it's actually the most resistance kind of as we go down, if that makes sense. And so if the blood has been injected out of the periphery and the constant current is going through tissue and muscle and bone, which are not as good of conductors as blood, then the lowest point is when the contraction should be, completed. And once that closes, then we can essentially start our new cycle. So that's what that's doing. It's no more advanced than that. So in the cases, a lot of times where people are interested in LVET and the left ventral ejection time, you will likely want to go in and be pretty rigid about this to ensure that you are in that correct trough location. And here it seems somewhat obvious, but in a lot of cases you can have multiple troughs that occur in there. And we would want to pick the lowest one. So that becomes a little ambiguous as to should it really be the lowest one or the first one, things like that occur. Which again is just one of the inherent issues with using the LVET, which is why most of the time we recommend pre-ejection period, why it's a little bit more common. But that's how that's calculated. Okay, and then yeah, there was a discussion sort of offline a little bit about moving V notches a little bit, so I'm just gonna harp on that a little bit more here for everybody. So a couple strategies we can take. So one is that we use the algorithm here for detecting that V point calculation. So this is what we mostly recommend for everybody, which is a percent of DZT plus time constant. So we're going to go 15.5% of the waveform, and then in this case apply a time constant of 4 milliseconds. So if the beginning of this starts at Q for everybody, but we're going to follow the blue line here, then we're going to go 55% of the waveform. So 0 being Q, Z being 100, 55% up, and then applying 4 millisecond time constant, and it's going to place it there. So the software is not looking for this slope change, and it's not looking for that dip, that trough. It is strictly based on, again, the sort of timing between what really starts is the R to Z, right? Because this Q is based off of it, but it's really based off that R to Z relationship on where V occurs. And get that out there. Okay. Yeah, so anyways, the discussion that was happening often, which is quite common, is in some participants, we can see that V notch. We can actually go in on a cycle by cycle basis, and we can actually see it in these participants, which can be a little bit hard to see in some cases, but I will turn off. So you can see in some of these segments, it's a little bit hard to detect here, but in others, we can actually see the notch that occurs right here. For instance, it's also being occurred over here. So we can actually see that on a cycle by cycle basis. If that happens enough, of course, then the ensemble average is going to have that same dip here. And so what we could do, the most accurate thing that can be done if we have, again, sort of disciplined experimenters that can make the same edit multiple times. Here. So what we can do is we can actually zoom in a little more into the notch location. And again, we can zoom in on sort of both axes. And okay, so the perfect thing to do here would be to put it in the point before it starts to increase, go up. So what we can do is we can train our eyes on the B value, such as the voltage here. So we're at 0.311. And all I'm going to do is follow this along until I see a rise and then kind of go back. So right there. So that would be the first point, sort of lowest point before the inflection starts to go up. And that would be the most accurate thing to do for pre-injection period. If we're looking at something like between subject analysis, either in that same session or even a longitudinal session, that person's going to express this B notch every time we do that. So this is something we could look at. But in a lot of cases, using spot electrodes, especially, a lot of participants will not exhibit this B notch that you see here, and we can see a couple examples if you'd like. But in here, it becomes expressed even more. But in some cases, a lot of participants will have this rise that goes straight up to Z, no discernible notch in any case. So in those, we would probably more likely rely on the algorithm, which is telling us where that point should be. And then in other cases, we would be manually moving them. And the issue just becomes, for between subject analysis is that we're using two algorithms all of a sudden. One is visual inspection for the lowest point of that trough. The other is that time constant of 55% up plus that 4 milliseconds. So that right there has been shown to be induce more variance than would be to just use the percent DDT plus time constant across the board for everybody, even when it's being estimated outside of that trough when it's visible. So in this instance, being estimated here, it's a little bright, but the actual trough being down here on this location. So that's our general recommendation on it all. There's a few different ways you can look at that and think about combining it all, but there is a paper, it's called Where to Be, Letter in TZDT, and in that it'll kind of give you the results on those studies and why they found that it's more accurate to use this algorithm than the visual inspection.
There ever be an instance where you would change the percentage from the TZTT way when you're using the beat point calculation method, like changing it away from 55%?
Yeah, I mean, there's different algorithms out there that'll, there's different publications and papers that have like a slightly different setting on how far they went on that. So if you're doing like a study replication or something, you can use that, but non-human primate models also would work as well. So be a little bit different. So they would have a different rise time essentially.
Yeah. I have a follow-up question to that. So I know that was a concern for our study, in terms of kind of like beat point location and sort of where that, if that percent peak in that constant would be appropriate for our sample. So what we did is we took the baseline events for which happened to be just the cleanest events for our study, and then we took kind of where the location was of where the algorithm was placing it, and then where the visible B notches were, and finding that difference. And then we took the mean of that, and depending on kind of whether it was placed, if the mean was like to the right or to the left, then that's what helped us determine whether we change the constant or the percent. But would that be something that would be advisable to do for your, is it worth going through the effort of doing that for your sample, or would it be something that you can be pretty confident that the 55% and the 4 constant set to 4 is something that you could use universally regardless of age? And
Yeah, just going back to kind of what we were talking about before, I mean, it's you're kind of creating a framework that is relative to the population that you're looking at. But if we use the same thing here, I mean, you're going to create a timing characteristic where you're saying this should occur at like 200 milliseconds later, say, for example. Well, why not just use this one as the standard approach too? You know, like it's going to be the same for every participant. So again, unless I was looking for something like within the subject, and we're going to look at how they're changing over time, because we could look at within and between. Then in one case, I would move it, and then especially if they have visual inspection or your method. In the other case, I would use the within a subject for the viewpoint calculation method. Yeah. Yes.
I have a related question, or maybe just clarification based on what Scarlett just discussed. So for between subject analysis, then is it always better to use that 55 plus 4 and not worry about the editing unless it's extremely noisy data?
Yeah, and so you know, if we were in a study where let's just say that everyone had a visible V notch, then I would just train people to look. I mean, that's not that difficult, right? To have them look at that lowest point until it goes up. There is sometimes 2 derivatives in there. You can actually see what looks like 2 notches. In a lot of cases, that can be one of those pressure valves like opening a little bit, some blood ejected. There can also be some blood coming back in, so which can create some of those notches. In those cases, then it becomes a little more ambiguous for the students as which one should I pick. A little bit more rare, but let's just say that you're designing a study where everyone does have that V notch, then I would just do that. But in other cases, yeah, I would certainly stick to this for this across the board, so you have more, you know, inter-rater reliability essentially.
Because I thought you also said this causes less noise this gives less noise in the data or less variation. Using this 55.
In how we're actually editing the data, like between actual like the human raters that are doing this, some of them are going to make different decisions again based off of like which V notch they believe it occurs, and there can also be the human error of just like not picking the right point. Pharmacological blockade, sympathetic nervous system at the heart is about 5 milliseconds. So that's our window with complete blockage. So you imagine like milliseconds are matter on this case. So if they're off just 1 or 2 points, that's going to change the pre-ejection period to something that is statistically significant. So creating a standardization is key there at that point. But let's say that like, you know, the sort of spot electrodes, everyone has a B notch, like it's never happens. But if you use the band electrodes, you have a good chance of getting the B notch on almost every single cycle. So if it's something that we absolutely needed, and they're children that aren't going to move around too much, let's say, where there's not a lot of motion artifact, then I think the band electrodes could be a good approach if we wanted to be super precise with it. Also, there is a thing in here which is I haven't quite discussed here, but the show range here next to the percent DT plus time constant. So what this is looking at is actually based off of the heart rate here. This is based off of a couple of very large data sets. I think it includes over 1,500 participants with ECG and ICG data using the same systems. And essentially there is a plausible range of pre-ejection period based off heart rate. Like if its heart rate is super high, then there must be some sort of cap at which point V notch could occur. And then same as low, that it might be a little bit longer off. So that range has actually been plotted here. So based off of this person's actual heart rate, the sort of dotted line here is the minimum time at which we expect that left aortic valve to be opened up. The dashed line, which is kind of overlaid over Z, is the maximum amount of time that can occur. So based off their heart rate, it is saying that, again, this is the minimum time, and that just happens to be right around where the V point is being estimated. The range estimation, though, is based off of adult subjects. It's not for children. So this is going to be quite a bit different for the children in that range. So if we're looking at this and this is really never making sense for our data set, we just turn it off. It's not anything that has anything to do with a different algorithm. They're mutually exclusive completely. It's just a visual guide to let us know where that B-notch should occur. But yeah, something else that can help you with that a little bit. So I'm going to go ahead and look at a topic file here, and I can move on to maybe that's unless anybody has questions for someone. Okay, so I am going to. I don't know what I touched. I'm going to start over. Okay, so a couple different things going on here that I wanted to show. So one is that we can see in this file that we have a sort of very thick band here of interference on the segment. And usually this is indicative of that electromagnetic interference we were talking about before. So this can be caused from a myriad of different things, but most commonly it is from a device that is plugged into the wall for the alternating current. So how the power grids work is that, so direct current doesn't travel very far. You have to keep amplifying it. It's super inefficient. So it comes with alternating current, which is essentially having these two power lines. We're going to induce current on one and the other 60 times per second. We're going to oscillate that. And one of the effects of that, though, is something called our acoustical harmonics, in which we can actually see that change of the oscillation between the two power lines and actually be seen as innervating our signal and cause this sort of issue that we see here. So in those cases, what we can normally do is turn on the notch filter that we talked about before. So in North America, our power grid oscillates at 60 times per second. Everywhere else in the world is 50. Of course, we're always different. And yeah, anyways, that can help attenuate that signal and get rid of that big band that we saw there before. This person also just happens to have some somewhat wonky impedance data. When I say somewhat, I mean very different. So yeah, anyways, you can see here that this is what I was talking about before. Even if we imagine that there is another normal rise to Z, now you have this 2 point notches. So that's why sometimes that visual inspection become a little bit of a problem. Of course, your approach would probably control for that, but still, that would become a little bit of an issue with manually moving these along. The range can help you quite a bit with that, of course, if you're looking at adult participants, but yeah, so just something that would cause this very difficult to use. And then the Z point over here. So that's that point of what's supposed to be the max blood flow. And what that is then going to do is this R to Z relationship or estimated B, and it's outside of that range which we expect it to be. And so in these cases, we normally would, not use that segment at least, because, there's something going on, such as this is not the correct Z point. As far as just the timing criteria alone, this being way over here, about 414 milliseconds is way off from what we'd expect it to be. So that's one indicator, but it also just looks abnormal compared to that sort of triangle wave that we're seeing before. So yeah, this can come from a couple of different things. The most common is just going to be electrode placement. So someone not placing electrodes in the right spot. Electrodes are dried out is probably 1A on those. That can cause these sort of issues, including the 60 hertz noise. If your electrodes are dried out, you can really receive a lot more of that alternating current saturating your signal. So making sure your electrodes are fresh, not dried out within their expiration date. If they are out of their expiration date, you can apply Gel. So just for those of you familiar with EEG collections, the same sort of electrolyte gel that's applied for those. And you can actually take this off and we can apply gel in the center of that. It's hard to get students to do this correctly, reliably. Some won't put enough gel, some put too much. We don't need to get a syringe necessarily and figure out exactly how much goes in a each sort of sensor is 0.22 milliliters if you want to know. But the thing to do is just essentially fill the cap up, and then when it goes on, we don't want the gel to squirt out. We don't want it to make contact with something else that could essentially turn it into an antenna. But if you have to, if you're out of sensors, everything's, you can't get new ones delivered in time. It is sometimes nice to have at least one of these around just to kind of rejuvenate those, if you will. But anyways, sensors being dried out being the number one issue, electrode replacement, and then there is also the case that this could be some sort of abnormality with the physiology. So as talked about before, there could be some sort of valve issue within the heart. There could be essentially back leakage of the blood. Let's check it out of the periphery. If those valves don't shut completely, we can see that come back in, which can create that sort of low resistance that we see in this area as well. There's a lot of different things that can occur there, but the last being probably the most unlikely, especially if you're in a sort of healthy population that you're studying. But long story short, this is probably something that we could not use for this participant. We can go in and we can actually look at the edit Rs. This would be our first recommendation before you're just like, oh, it looks weird in the ensemble, like nothing's usable. We would again set our 10-second window and start to look at these data in the beginning to see if we can look at this a little bit closer. In this case, this is actually someone that does have a little bit of an abnormality going on. You can actually see from a larger standpoint here. Maybe if I don't make my window quite so large, and I will hide everything else. Let me hide these. That's enough. Okay, so I have what is Z0. That's that first baseline measure of impedance cardiography. DZT being the first mathematical derivative of that. But anyways, the Z0, we like that because we can actually derive respiration from it. So you can actually see here there's a perfect trend between the respiration that they're taking, which has a abnormal sort of double hum structure on that as well, and then the change in the actual amplitude of the DZT there. So essentially every time we're taking a breath in this person's physiology, we're also seeing that the change in amplitude of the impedance signal is occurring quite a bit more than it should be. And so yeah, just due to some potential disease state this person has, it's just occurring for every single cycle. So if we were to zoom in, if we were to turn our ECG back on, we would just see that this is something that we're not going to be able to use for any sort of cycle because we have sometimes we have a peak here, then in a lot of cases we have this flat shelf. And so enough of these cycles, which are not that defined crispy, created within a segment is going to result in an ensemble average, which has that same thing. So what we would normally do is we would go in and try to edit those out. So anything that would not look sort of to our ideal triangle wave, we're going to exclude. So how we would go about that is to come in here and simply look at that cycle that is following our peak here. So one of the criteria would be that Z has to occur after this R point. It's physiologically impossible for the blood flow to occur before the electrical command telling the heart to beat. So if we look at that peak, the first one that occurs afterwards, then we would try to take that approach to say like, okay, there's a singular point there, there's a Z, I'm going to leave that R peak there. And then for these instances where we see these flat shelves or sort of a lot of wonkiness to the signal where we don't see that peak, then we're going to delete the R peak that precedes it. So for instance, if I was not interested in using this one because of all those, or these three, I guess I just talked about, need to edit -G. We can remove those, and it is going to throw up an alert letting you know that there's a very long interval within here, but we've already done that IVI calculations and RSA analysis in HRV, so it's really not a problem. But what it's going to do is if there is not an R peak, it's going to ignore any of the impedance data that follows it until the next cycle. So from this point, it's going to use that one that precedes it, that Z peak, and then from that point forward, all of this is going to be unused until that next peak. So this would be the procedure that we would take if we were trying to clean up that ensemble average enough to where we can actually see a singular Z peak. We don't have those two potential V notches. But if we jump through this file, I've looked at it a couple hundred times doing this. It occurs that it just happens every single cycle with this person, so it's not due to motion artifact. It could still be due to something like the electrode replacement dried electrodes, but it's occurring every single cycle, and I just happen to know this acquisition. So if we do that, it doesn't really matter how much we remove, you're always going to get the same morphology. So this particular person, we cannot use their repeats data because of all those reasons, but there are some that are in between, and so those can certainly become a little tricky for to get consistently. One thing I'd recommend if you can't hash that out internally and come up with like an agreement between people is, especially if you use mine where you pay for training, again, you have the complimentary training. We can just sit down with you, 1 hour if you need to per day and go through your files. A trainer will help you with those, and then yeah, clean up those are very messy ones. But yep, that's kind of all on that. Again, we'll go through quite a few examples tomorrow. So again, I know this is pretty quick here, but you all are supposed to be advanced, so. Okay, so now we're gonna look at skin conductance, and then we'll kind of wrap up. We've got about 27 minutes here. Actually, those are all on top. All right, so let's go back. Okay, so again, all of the events and modes are going to be identical to their applications, except for continuous mode and HRV. Calibration settings. So this is grayed out because it's our device. We know the microsiemens to volt conversion. So that is, if you're loading a file from a different acquisition system, this will highlight and let you change that. And then I would just consult the manual for that hardware to figure out if they're actually collected in volts, millivolts, microvolts, what have you, and then just do the conversion to microsiemens per volt. But anyways, so microsiemens identified here, little u, big S. The first thing that we're going to look at is the potential for a skin conductance response. So we have a couple of main things that people are interested in reporting or looking at, observing for skin conductance. So first one is mean skin conductance, meaning maybe the most popular, so just the average level of skin conductance within the segment. This is like the most robust and metric of skin conductance because it is not as susceptible to any sort of movement artifacts. Signal dropouts are still a problem, but it is quite flexible if we needed to sort of edit the waveform. But in addition to that, we can look at things like the skin conductance responses. So that's actually being identified here as a potential spontaneous sympathetic activation. And what the qualifying criteria of this is that we have a sort of trough and then a peak, and this rise is going to have to be based upon this criteria on the calibration settings. So 0.05 microsiemens or above, it's now going to be identified as one of those skin conductance responses. And then from there, we can also look at event-related skin conductance responses. So that's being seen here as the min and max window. So that's that 1 to kind of 3 second window I've been talking about before. So if we actually were to look at a file that does have these events, we can turn them on. It's going to do multi-event here. Okay. So I think. All right, perfect. So on this segment here, we have an event that occurs right at this file section right here, and then we have an SCR that is it right afterwards. So it has to occur 1 to 3 seconds after the event occurs. So this rise has to be within that window, and then again that 0.05 or above from the trough to peak has to occur. If those two criteria are matched, then it is considered an event-related ischemic response. So it is sympathetic activation due to that event onset. Everything else that is does not have event correlated to it and doesn't meet all those criteria, well, just the criteria of the timing 1 to 3 second window will be classified as a non-specific SCR. So if you're in a study that you do not have any sort of events that we are expected to be related to some sort of sympathetic SCR, then you know, they would all be non-specific essentially. Okay. So respiration would be the next thing to look at here, and I'm going to look at a smaller window. We'll go back to time. Okay, so what we're looking for here is we want to see the difference between sort of the psychologically driven SCRs and sort of the behavioral nature versus ones that are just due to respiration. So if we actually take a deep breath or a sniff or something, we can create an SCR which looks identical to that that was not induced by respiration. So the idea with the respiration here is that we're going to look for one that occurs again about 1 to 3 seconds before we see that rise in that SCR. If that does happen, then we, in most cases, want to remove and delete the points for the SCR so that it is not included in our total count. And so, yeah, it's in one thing that's here is a little bit, there aren't a lot of rules and regulations around it, as you might know, and look at this. So when editing, the general recommendation is do as little as possible with this. And so unless the signal is very messy and we have a reason to edit the data any further, we usually don't touch it. But our general recommendation is if the respiration is about 2 to 3 times the magnitude of the surrounding respirations, that is where we would actually look and say that if there is an SCR within that 1 to 3 seconds after the trough, so 1 to 3 seconds after this, there's a rise in this one, then we would actually delete that corresponding SCR. So I'll show you what I'm talking about here. So this one, in case it's fine here. So let's look a little bit closer at this one right here. So we have a very deep breath. So this is essentially making this magnitude from the trough to peak about 2 to 3 times larger than the surrounding ones. So then what I would do is essentially come in and I'm going to mark the point at which that respiration begins. So here on the orange, and then we're going to look at the same points on the SCR where the trough occurs. Again, looking at the delta, it's less than 1 second, so then I would leave it alone. But if it occurred that that SCR, let's say, was over here in that window where that trough actually started to rise, then I would delete the trough and peak points to remove that as a valid SCR. So there are other techniques here. As far as if there is signal dropout, I can go ahead and create that for you. I have some additional examples I'll show you tomorrow of this. But I'm going to leave my respiration alone. And I'm going to essentially just remove these data here. And yeah, so this is hopefully not super common. Happens a little bit more with kiddos, but when they sort of pick the sensors up or rip them off completely. But it can also be the case that is just from improper electrode placement, or not placement, but the electrode is kind of coming off the skin because the adhesive's old, or they move their hands too much and it starts to come off. There are some pictures that I can share with you tomorrow for children with the smaller hands. The larger sensors become a little bit of a problem because they don't fit on there correctly. So what we can do in a lot of cases is we can cut these down. These aren't the right sensors, but for the example, we can actually cut around it down to just leaving that center where the electrolyte is at alone. And then what we can do is we're going to take paper tape and we can essentially just tape across those to keep those on the hands. This can be helpful for adults as well if they're, again, like sweating a little bit more than normal. The sensors can come off, so we'll just kind of tape over those. We will show an example of that tomorrow. Participant, hopefully have somebody, otherwise it'll be me. And we'll kind of tape those and show what that looks like. But that should certainly be one issue in which this could occur. So when we see something like this, what we would want to do is edit the peaks and troughs. and we come in here and we're going to find a point. We should probably zoom in a little bit more so we can be specific about this. And yeah, in a lot of cases, it's easy to sort of just pick this point right before that drop off, and then when it comes back on, it does, and then we're just going to spline those 2 points together. If this happens to occur around an SCR, such as like when we edit this, then all of a sudden it creates a peak. In most cases, we're going to just remove that SCR because it's the edit that created that. But it can be a little bit ambiguous, of course, when this occurs. So let's just try to minimize this as much as possible. So yeah, that's one tactic that can be done if we actually see that drop out completely. Another thing that can be done, again, there's a lot of different recommendations on this, depending on the context of the acquisition. But if we did have something to where we had a very messy signal essentially at the beginning of this, we can do something like extending, from something like around the mean of this baseline point across to the other side. And then that is going to create that sort of flatline procedure at that normal baseline. Again, there could be a lot of statistically significant improvements by doing this kind of thing. So I would certainly use a caution, and when you know essentially what you're doing very carefully. But that is another method that can be used, especially if the issue that occurs is right at the beginning or the end, and we don't have those. We don't have the ability to put our X cursors on the sides and actually say, spline across. We don't have that at the beginning, so we can pick a point right at the end of it to use that extend feature on. So for example, if we have this one here, and then all of a sudden this drops off completely, well, we can't go to the next segment and then say spline. We're kind of at that point already, so then we could say essentially from this point forward, we're going to extend over to the rest of that segment. So again, this procedure right here, if you're looking at tonic level, so there's tonic and phasic components of this. The phasic component is going to be from this top point to the half recovery point, which is a time measure. So anything under the area of this curve right here is the phasic sort of activation period. Anything outside of that, so from the half recovery point to the next trough, is tonic. And so if we were looking to for an tonic sequence level or the tonic period, then this extend feature probably should not be used, nor should the spline, because we could be essentially removing a skin conductance response from that area. So total SCRs and tonic period, tonic SCL, I would not recommend if we have to use a spline feature. However, if you're looking at just a mean skin conductance, then again, with caution, that can be normally acceptable.
And the extend is more for the beginning and end of the segment versus.
Yeah, because otherwise you should
I think
be able to
just remove the points as well, and it won't be included. Like just
yeah. I mean, if you were saying like for some reason like I spline it and all of a sudden it's created an SCR because of that, we can just go in and delete those 2 points, right?
That's correct.
Exactly.
So if we need to spline at all, is your recommendation just not to use tonic? Or is it just that if you're splining an excessive amount?
Yeah, I mean, I would try to keep it to as little as possible with that. I can't give you a number, fortunately, because it's skin conductance. It's like EMG, which is like noise or something. But try to do as little as possible. I would certainly try to keep it below like 5% on those. But you're going to underestimate, like if you remove an SCR, you're going to underestimate your total SCR count, and it's not even going to be standard within that person for different conditions. So it's pretty risky to do such a thing. But if you can spline an area that you're pretty confident there was an SCR that occurred in that time. So let's say there was a very small drop off in which the skin conductance response couldn't even occur because it's like within that 1 second window. And I think you're pretty safe to spline those because it couldn't even physiologically occur within that window. But outside of that, yeah, I would just recommend just looking at mean skin conductance, which is usually a pretty safe bet. Again, if you're looking at children data, it's just messy and stuff like that, and we have all these different SCRs that are occurring. A lot of times when we see motion artifact, though, it doesn't look like a skin conductance response. There's sort of a lot of jagginess to it compared to this nice sort of rolling hill architecture we see here. So in those cases, we can usually spline out those motion artifacts if they're significant enough. In a lot of cases, like when we see a motion artifact, it's not really adjusting too much with the mean skin conductance. It's usually on like 1/100th of a decimal or something like that. So in those cases, I usually just leave it alone unless the artifact is pretty egregious. Yes.
I think this is an impossible question. If you don't have respiration data, is there any way, based off the wave architecture or morphology, to try to determine if it's a valid SCR, like something that's indicating SNS activation or reactivity versus respiration?
An impossible answer.
Yeah, I guess it's not impossible, yeah. You don't have a magic solution.
No, there's not, unfortunately. Yeah. So in those cases where you don't have respiration, like let's say you have like a watch or something, like a Apple watch, like that would just makes no sense. Yeah. But this can be another sort of case example here, where we see this huge rise to this level, but we actually can't see the other side of it. Like, so if we can go over and actually see what occurs there, that's helpful, but that's probably a skin transverse response, right? It's just a very large one. And it's unfortunately bridging these two segments here. And so because this is not being included in there, this is one where I would spline that across, being cognizant of that level when we do that. So what I mean by that is, here is our sort of return baseline, if you will, from that point over there. So we are, right there about 6.67. I didn't have to do that for both, but I did. So 6.677 on that area there. So then we can take that high cursor at that point before that drop occurs. We can extend across. And then we would want to do that same thing as we did before, forget the number. 6.8, let's do 6.8, it's fine. And then do the same procedure over here. And we can actually press. And then from that point, we would just intersect that with that first return down and extend over from that point there. Oh, did it not work? I don't know if that's the right value, but okay. So that would probably be the procedure I would take if there's a very high skin temperature response that occurs, and just bridging those. Happens again, this person's sort of annoying a little bit in the case, but thankfully we do have the peak there, so we can use that as an SCR. But this is a procedure that can be taken again if there's a very significant one that is kind of right in between. You can also look at it differently. So if that's occurring, you could look at more data. So, this regulation of the 60 seconds does not have to follow the stuff that we had before. So, if there's something like within a baseline, there's a 5-minute period, you could just certainly extend that segment time up to something that would encapsulate everything, and then we don't have to necessarily worry about the fact that our segmentation is creating something like a increase or decrease of SCRs. And then we can kind of just look at that from this approach here, which might reduce some of those unnecessary extensions.
Yeah, there's an argument to be made to just edit the entire file, like zoom in 30-second or 60-second chunks, rather than like creating 60-second segments that might artificially create or remove SCRs. Just tell your editing team you're going to edit in its entirety, zoom in so you get, the visual acuity that you need. And then after it's edited, you go back and change it to segments for writing out. Or
I mean, certainly the approach is a little labor intensive, but it's just
everything with CPA is labor intensive. Data is just like you're on the mark.
simplest thing in the world is just sweat.
Yeah. It's always, I feel like EPA is not giving its flowers for how complex it can get very quickly.
Yeah, everyone kind of stays away from it a little bit. Yeah. So it looks a little bit, the sort of problem with it is just like looking at and correlating respiration, just visually, like looking at this kind of thing is a little bit difficult. But then, also zooming in, you're going to have this zoom window and you're like moving through here, and then the respiration is kind of spread out, so it can be a little difficult there. But non-stationary using the data is probably the reason that you don't want to do that. So that is where, which like the data in the beginning are just statistically significant, different than the ones at the end of the segment. So if we're looking at a very long epoch of something like 10, 15, 20 minutes, you can certainly see that in all the different physiological waveforms. So that would be a reason why to break it up into different segments, and then you can look and see if there is any sort of significant sort of change score between segments. And if there are, you would like likely want to reject those ones that are outliers. Again, sort of 3.5 standard deviations from the mean. But yeah, that would be the big reason. But one approach you could take, if you wanted to do something like that, would be to use the calculation method, turn that interval onto something like the 30-second windows that we had before. So we're going to then follow the 300 seconds segment or whatever you chose here, using those intervals at 30-second points. And then we do look at the mean skin conductance in itself. We will actually be able to check this up and look at the values between them. Not super helpful at this point because we can't usually do that math in our heads, but on the output, you would see a different book that would be created that would show you all of these different segments and their values, and then you can kind of plot those to look for significance between them. So another approach you can take, but it still has the other pitfalls that we talked about here before.
And then just to clarify, because I feel like I missed this, this is kind of the answer to first, you're suggesting me outputting it all like in one larger segment as opposed to just a smaller 30-second segment. That makes sense because something that I observed is that I think when I view a whole task together, it gives me a good sense of like when we have lost signal. And another thing that ties into Lindsay's question is I noticed that we when we're creating outputs in 30-second segments, sometimes the 30-second segment cuts off the skin conductance response, right?
Right.
And so the approach that I was on a call once from a different team member from MindWare, and they were saying that if you don't see the trough, that you're better off deleting the peak. If it's like cut off, right? So like let's say you have a skin conductance response, and it's being cut off, and so the trough that is typically paired with that peak is invisible.
Okay.
You shouldn't count it within that segment, so you should just delete the peak. Is what they suggested at the time, but I don't know if that's something that clearly outputting it all in one larger chunk would get rid of that problem.
More, right? I mean, you're still gonna have the problems like here, but you're dramatically reducing it for sure. Yeah, I mean, it's certainly good. I mean, that recommendation is not wrong. It's just so contextual. It's like dependent on how you ask the question, what was the different questions they asked. I mean, there's so many different things within it, but the most important thing with skin conductance is just being, standard with every single thing. Like we're gonna do it the same way exactly every time because then it's just all relative to your study. So.
Well, it's not like you have to pick ahead of time. I think I put this in my editing manual. Which outcome measure?
Yeah, absolutely.
You cannot have all the PA measures. So if you're focused on SCR, cool, we edit this way. If you're focused just on SEL, then we're gonna edit this way. Because otherwise you have to like edit the same file multiple times.
Right.
Or, like I'm editing for SCRs and now I'm editing for SEL. And now I'm losing my mind.
Yeah. or get halfway through your subject pool and then realize like SCRs are unreliable.
Yeah, you're
because
don't trust the SCRs because no one can get reliable with editing this. And I've gone through different headaches of like zoom out to look at the whole morphology, whole like architecture of your task. Now zoom in, okay, and then zoom out again.
Yeah.
And then
This is me venting now. This is not helpful.
I think many of us that do this are right there with you.
Absolutely, so hard.
and I have to answer your questions, okay? What about me? So another thing that certainly very long studies that are spanning like multiple seasons. I mean, dehydration effects for in the winter versus the summer, those are going to take play in this as well. And so something to think about. With skin conductance, it makes it a little bit even more fun. So.
Have you noticed with elder, like there's a lot of movement artifacts with really young populations, but then when we're talking about really old populations, we have a different kind of skin conductance.
Yeah. The epidermis hydration levels decrease as you get older.
Or even if you're hydrated, their skin just isn't as hydrated.
Yeah, exactly.
And you use the special soap and you wash their hands and you take that thing on.
So one thing, which is going to probably not be an option for anybody here, but the perfect recommendation for skin conductance gel to actually innervate the sweat glands is 30 minutes. I think almost there's, we don't have that kind of time, even if you put it on them right away.
Right.
But if possible, I mean, I don't know if you could, I mean, you have them in there that
We
long, but
have
I don't know. But
it does make a huge difference.
if you can wait 30 minutes, that's normally
Before
the
you
way to
do
go. Other than that, I mean, normal approach is 5 minutes. But I would not slap the sensors on and do the baseline right away. If you have to do anything first, I would at least just put the electrodes on and you tape them on their hands, like right after they sign the consent form. And then, because later on we can snap the leads on here. This isn't really that painful in the hand. There's not like a lot of tissue there, but you don't want to do that anywhere else because then it really can hurt to snap that lead on afterwards. But that's an approach you could take to make sure you have at least that 5 minutes.
So you're saying that by having this sort of resting period with it on before you even start collecting the data.
Yeah, that was the example I had earlier. We have the sort of surveys, consent form stuff, and then there's a resting period, which we don't even really use, and then there's the baseline.
Okay.
Yeah, but or just make sure there's 5 minutes in between.
Okay.
But yeah, the 3-minute thing.
Yeah, we noticed that with that last study, we were slapping them on early, to try to get the data around the meal challenge, and it's just like, it's not feasible. I spent so much time on it, throwing it in the trash. But the stuff related to the anger recall task later, when the electrodes had been on the hand, is a lot better and more usable because of that factor. Because it was just sitting there on the hand longer. It was too long. Some people that are really sweaty, I had to replace them and make sure that they sat on the person's hand for a good chunk of time before that task. But that's only for like the hyper sweaty people where it's falling off very now.
Yeah, and another thing to consider if we are like exclusively looking at elderly population is like don't take it from the hands.
Yeah.
Like,
What do you do more for the wrist or for the feet, or what would you do?
I mean, not the feet or hands because you're gonna have that thicker layers of the skin there, but like the wrist is nice, or even the shoulder, because the skin is much thinner at that point, so we actually can get those sweat activation still from those areas. But you have to again know about you're gonna do that ahead of time.
It's the whole population.
Right. Yeah.
So if you were doing a study that had sometimes our study will range from 20 to 90, right? We're trying to get everybody we can, right, within whatever, and we'll group them. But then I would just do everybody's electrode based on like I'm doing them all the 90. Yeah.
I mean, the wrist is and it's pretty successful movement artifact depending on your protocol. So if that's not an option, I mean, like the shoulder is okay. Like it's weird though, so you gotta be very kind of careful when you're doing this and writing it out before. It's like why are you taking it from the shoulder? All of those reasons are reasons to do it. I can send you the sort of source literature that you could reference when doing that kind of thing. But don't just do it because they're gonna get a revised reason immediately for that kind of thing. They're like, why did you do this? Why did you take it from the hands? One thing that can help is you actually have the highest skin conductance readings from the fingers. So we normally take it from the palms of the hands. The fingers actually give you a little bit higher reading, so more susceptible movement artifact again. But if you're taking like blood pressure like where their hand is stationary, or we can just strap their hand to a table or whatever, then the fingers can actually work a little bit better. So that right there approach wouldn't then get any sort of red flag questions. It wouldn't have to do any sort of reversions. But if you take it from the wrist or from the shoulder, you're going to get much lower levels of everything. You're going to have to lower your threshold for skin conductive responses and everything. Now I have that literature that will tell you what that would be, because there are studies in which they've actually looked at the individual sweat gland concentration across the whole body, and so that we can actually know that offset. Another thing you can do is like take it from both at the acquisition, and then you're going to just transfer over to that, and then you have a ratio conversion.
Will you go over tomorrow placement on the shoulder, like kind of like traditional?
Yeah, absolutely. I'll bring up the pop and we'll just look at it. We just put it all over. Yeah.
I know you spoke about other like alternative placements for impedance choreography too, so I think that would also.
Still electrodes everywhere.
Yeah.
Yeah.
Who's this volunteer? Who is it? You? Yeah, we
I'll
can.
make sure to wear a t-shirt.
Sure. Of course. Okay, like sport 1. I ended up I've never done in my life.
Good job.
Yeah, you were keep talking. I was like, shut. Does anybody have any other questions before we end for today? No? Okay, cool. All right, well, thanks for everyone that's coming. Hopefully you come tomorrow. See a little bit more of this. I hooked up 1,000 times for.
Thank you. Can you explain a little bit about how tomorrow's gonna be different or?
Yeah, so I went like hyperspeed through the
Yeah.
analysis here.
Okay.
In that, what we're gonna do is we're gonna spend like the entire, barring some weird lunch thing that happens, 3 hours of just going through them very slowly. And so yeah, you're gonna get a lot more of like, okay, we're gonna load the file, or the edit, and have like some more techniques, and we're gonna see more topic examples and things like that. The morning session is the same deal, but we're actually gonna do acquisition, applying sensors, going through that whole protocol. There's additional tips in that of like washing their hands, all these things that I didn't have time for today, but just sort of comprehensively acquire and analyze data.
Great, so more from the basics.
Yep.
Okay.
And I would have done it the other way around, but it just, yeah.
Okay.
That's how I had to organize it
No
here, so
worries.
advanced then basic.
No worries.
Awesome.
Thank you so much.
Of course.
Yeah.
Well,